thanks for having me here. So yes, whenever you want, just go take coffee, tea, so that I can also understand, like, when you start not making it anymore and I see all the people migrating to the coffee room, then yeah, that's probably time for stop. Anyway, let me just go back to my slides. Here it is. So this is what we're going to talk about today, in vivo neuroanatomy using diffusion MRI. And I'm Matteo Bastiani. I'm now based in Nottingham. I'm a research fellow in Nottingham, and I also hold an honorary position at the Wellcome Centre for Integrative Neuroimaging in Oxford, so the FIMRIP Centre. Just for me to get a rough idea, how many people have used diffusion MRI so far? All right, cool. fMRI? All right, interesting. Okay, let's see whether I can make myself clear by the end of today. Anyway, just to start, can everybody hear me also at the back of the room? Because I have a very low tone of voice. Is there a microphone I can use or no? Okay. If you don't hear me, just show me. Anyway, to start, how do you usually do anatomy? If you're interested like in gross anatomy or the microscopic characteristic of the human body. This is what I call the old school, right? So this is my tribute after spending 7 years in the Netherlands. This is the Rembrandt anatomy lecture of Dr. Nicholas too. And typically, to learn about anatomy or neuroanatomy, you need 3 things, right? The teacher that explains you the stuff, so the professor, the book from which you derive all the knowledge, and most importantly, the guy in the middle, the cadaver, right? Which is probably from an ex-convict and something that you could sacrifice, but it has been killed, and then you can, basically look at anatomy. And also the nice thing that you can see in this specific painting is what also interests most of us as neuroscientists, is that we try to connect structure and function, right? So the professor is showing the muscle, saying this muscle is responsible for making this movement, right? So this is the link, this is one of the most interesting links from the neuroscientific point of view. Nowadays, we just need to spend a little bit more money, but we can get these fantastic machines, the MRI scanners, right? And what these scanners allow us to do is that we take the cadaver out of the picture finally, and we can start doing neuroanatomy in vivo at an unprecedented resolution, right? And with multiple contrast as well. So here, what I'm showing you is, a typical MRI scanner on the left-hand side, and then I'm putting you 2 axial slices from the same brain, telling you that basically what we can get from the MRI scanner is with the same machine, we can get different tissue contrasts, right? So these are the most typical tissue contrasts that we can get, the T1 and the T2 weighted scans, and you see that already it becomes pretty clear to separate the 3 different tissue types, right? So corticospinal fluid in the ventricles, deep white matter being hyperintense here on the T1, and gray matter being slightly darker on the T1, and a different contrast, almost flipped, completely flipped, on the T2 weighted image here. So same brain, same machine, but different kind of contrast, different kind of neuroanatomical information. These images are typically in the range of 1 millimeter isotropic, and if we think, based on what we know from these kind of pictures, so from electron microscopy picture, we know that in each and every of these voxels, which is how we call the spatial location in the MRI images here, which is a 3-dimensional pixel, effectively. We know that inside each and every one of those, we have thousands of myelinated or unmyelinated deep white matter, like in that case, axons, right? And at least when it comes to diffusion MRI, so from my specific point of view, so from the specific point of view of what we're going to talk about today, these are very helpful for us because they do act as barriers and as cables, right? Because they're nicely organized, tightly packed together, and they follow a certain orientation. They make it such that the water molecules will preferentially diffuse along the orientation of the axon rather than perpendicular to it, right? And now we're going to see in the next couple of hours how we can use this information to probe about neuroanatomy in vivo. Because what we're doing effectively when we acquire MRI data, is that we're looking at these guys. We're looking at water molecules, right? That's where the contrast comes from. We're not getting any signal from the neuroanatomical substrate per se. We're not getting any signal from the axons, but we're just getting signals from the diffusion of the water molecules. And since we can do that, now we can start playing, now we can start identifying once again the 3 tissue types that I talked about before. So we have free diffusion, once again in the ventricles here. We have a slightly, well, still free diffusion, but more constrained in gray matter because of the cell bodies, glia, and so on and so forth. And most importantly, most interestingly, at least for the beginning of this talk, we do have diffusion in white matter that shows clear anisotropy, so a clear orientational preference. Because once again, of these tightly packed axons, the water molecules will diffuse more preferentially along the axons, right? So this is when we talk about diffusion anisotropy, and we mean that it has a directional preference. And knowing this, assuming these different behaviors of water molecules in these free tissue types, for example, what we're most likely interested to do is to sample a three-dimensional space using n orientations. So I want to see for each and every orientation in a three-dimensional space how water molecules diffuse. Do they like in that specific location, do they like to diffuse along this orientation, and so on and so forth, right? And when we do that, this is what we get out of our scanner, right? So we can play, there are two main parameters in diffusion MRI. One is orientation, so spatial encoding, and the other one is the B value, so the diffusion contrast. And here I'm showing you like 6 different images. In A, you have the so-called diffusion encoding gradients, which are completely turned off. So I'm not looking for diffusion in the first image, and that is just a typical T2 contrast, what I discussed, what I showed you about before. Now, what happens for the green dots? So when I probe diffusion along 2 different orientations, along the x-axis and along the z-axis, well, what you see here, what you should be able to see here, is that given the same slice, given the same axial slice, if I probe 2 orientations, the contrast of the same image change, right? So I'm looking at the same thing, but now I start having directional encoded information, right? And if I play with the B value, so with the so-called diffusion contrast, you see that from the minimum, so from D, from a B value so-called of 1,000 to 3,000, I get lower SNR, so it becomes more tricky to, even see that there's a brain in those images. But you see that it becomes more clear, the contrast to noise ratio. So you see that the hyper-intense areas become more intense, and the darker areas become more, darker, the higher the B value that I get. And it's basically like in photography, when you leave a shutter open for more time, you capture more light. Here it's the same thing. We listen to the diffusion signal for longer, and we capture more diffusion, right? That's how we enhance our contrast to noise ratio. And now what we want to do, given these images, is to try and go back, right? Is to try and understand, try to link these images to the neuroanatomical substrate that we know is there. And how do we do that? And the answer is with math, a bit of modeling. So I hope I'm not scaring anyone away already. But what we want to do with modeling is that we say that given the signal S for a certain orientation G and for a certain B value B, we try to link that with the signal with no diffusion encoding, so S0, and the exponential of, once again, the B value, the orientation G, and then you see the D, which is the so-called ADC, apparent diffusion coefficient, that will become later on in this slide the so-called diffusion tensor. So that is what we try to estimate. We try to estimate, again, in every voxel, that quantity D, which can be either a scalar, so the diffusion coefficient, or a diffusion tensor here. And just by this very simple equation, if we apply that and if we can recover D with some math, we can do some pretty spectacular things, because we can construct an equiprobability surface of diffusion, like I'm putting here, that will allow us to, once again, distinguish between the 3 basic tissue types that we have, and will also give us the so-called principal diffusion direction, right? So given the D, which in this case is going to be the diffusion tensor, I can now start to put these vectors into each and every voxel that I've acquired, right? So now I have the information that here, water molecules tend to diffuse from the front to the back of the brain, right? And so on and so forth for all the other spatial location. And we go back to the original assumption, is that now we say that this principal diffusion direction should correspond to the orientation of the white matter fibers throughout the brain. And given this assumption, we can start connecting the dots. So we can start from the left hemisphere and follow connecting all the dots, all the vectors along the path. And if we do that, we do what is basically known to be a structography. Right? So we can extract now from an in vivo sample, an in vivo human being, we can start constructing the long-range axonal connectivity in a non-invasive in vivo fashion. Right? So we can have callosal fibers, like in this case, connecting the two hemispheres. We're not just limited to that, so we're not just limited to a structural connectivity aspect, but what we can also derive from the diffusion tensor and other techniques that are available using diffusion MRI data is that we can infer, we can describe microstructure. Microstructure being the characteristic of the white matter axons that we have acquired that belongs to this specific sample. So from, for example, the most typical measures that are derived from the diffusion tensor is the so-called fractional isotropy, mean diffusivity, axial diffusivity, and radial diffusivity. Axial diffusivity being the amount of diffusion along the principal diffusion direction, and the radial diffusivity being the amount of diffusion perpendicular, so the D perpendicular, in respect to the white matter axons. And FA effectively telling us how sure, how confident we are about the estimate of our principal diffusion direction. Right? This is why it becomes much more intense in white matter. It becomes easier to distinguish white matter in respect to all the other. Because in white matter we have, once again, the densely packed axons, and the principal, it's going to be easier. We're going to be much more sure about the estimate of the principal diffusion direction than anywhere else in the brain. Again, we can apply the same tractography rationale that I just described before to extract several white matter bundles from the brain in vivo. So those related to language, those related to motion, sensory information, and so on and so forth. And we can start building in vivo atlases for all the subjects that we acquire. So that in the end, what we can do with computational diffusion MRI are mainly these two aspects. So we can do in vivo virtual histology, but we can also do in vivo virtual dissection. So the structural connectivity information and the microstructure information. Right? These are the two main aspects, these are the two main goals when it comes to computational diffusion MRI data modeling. So this was just a very quick and brief introduction. This is what we're going to cover today, at least in the first part of the talk. Give you an idea of what is diffusion and how we actually acquire the data. So we perform diffusion-weighted MRI. The diffusion tensor model, which I just now briefly hinted at, and DTI. Then we're going to go to the distortion correction, specifically for diffusion MRI, all the way down to how you should perform automated quality control once you acquire your data. If there are any questions at any time, just raise your hand and let me know. We can make this interactive. So as soon as something is not clear, just ask. Anyway, what is diffusion, right? So diffusion was first discovered by Robert Brown some time ago, and it basically describes the random motion of water molecules given a certain temperature, right? So they lie perfectly still at absolute zero, but the human body is at around 37 degrees centigrade, so water molecules tend to randomly diffuse with a certain diffusion coefficient, right? So he first observed this phenomenon. The person who actually formalized it, so put this down into an equation, was Albert Einstein, describing the mean square displacement as being dependent both by time and on the so-called diffusion coefficient, which is what I already have talked about in the brief introduction that I said. So that being these equations valid for any homogeneous barrier-free, so without barriers, so without the axons that I just described before, the longer you wait, the more diffuse you're going to observe of your water molecules, right? And this, of course, follows, as you can see here, sort of a Gaussian profile, two-dimensional Gaussian profile. So, exactly like I said, another way to basically describe exactly the same equation as before is that diffusion displacement well, an ensemble of water molecules diffusing can be modeled using a normal distribution with zero mean and a standard deviation equal to 2 time and diffusion coefficient. Zero mean displacement, so that's the mean of 0. And again, like I said, you have a double dependence, 1 over time, so how long you're willing to wait to observe a diffusion, and the diffusion coefficient itself. Why are we interested actually in observing this diffusion? Or we go back to the original introduction slide, right? We have said that we can easily at least identify, easily think of at least 3 different behaviors of diffusion in the 3 different, well, the 3 basic tissue types that we have in the brain, right? So we talk about purely free diffusion in the ventricles. We can identify diffusion in gray matter, restricted but still relatively free. And then we can talk about anisotropic diffusion in deep white matter. And the nice thing of this, why this works, is exactly because given the prototypical representation of a myelinated neuron, the axon acts as a barrier, right, for these water molecules. And if you were to look at the same kind of simulation profiles that we described before, we can see that the longer you wait and given a certain diffusion coefficient, those are the 3 different displacement profiles that you will experience in the 3 different tissue types. Being the anisotropic sort of cigar, giving you this cigar shape, showing you the anisotropic behavior of water molecules. So one thing is performing sort of a more chemical experience in which you're actually interested to measure the diffusion coefficient of different fluids. Another thing is deriving the diffusion coefficient from an MRI experiment, right? And this is why we talk about, actually, when we talk about diffusion MRI, we talk about apparent diffusion coefficient, right? It is apparent because it is dependent on the settings that you impose on your MRI scanner. So, given 2 different scenarios, let's say, in which you have totally free diffusion and another one in which you introduce a barrier, like it can be, for example, 2 axons very close to each other, and a single water molecules that can diffuse throughout a certain amount of time, you see that if you were to record your signal after a very brief time, the two displacement profile look almost identical, right? But if you're willing to wait a little bit longer, you see that these water molecules, the delta X of these water molecules, will definitely be bigger than the one you experience when you start inputting some barriers. So if you're willing to wait a little bit longer, now you can distinguish between the 2 different scenarios that we have here. One being totally free diffusion, and the other one being diffusion with actual constraint. And again, this is exactly then why we talk about apparent, right? Because given the different time that we set on our scanner, we can mathematically estimate the diffusion coefficient at every spatial location in the brain. How do we practically do this when we sit behind the scanner console? Well, what happens from the acquisition sequence point of view? This is from what happens from the physics point of view, right? So this is the actual sequence that you use when you're interested in doing a diffusion MRI experience. It's the so-called pulse gradient spin echo sequence. And what it basically uses, forgetting about the 90 and 180 for now, it uses these two diffusion encoding gradients. But basically what they do is that the first one labels the water molecules at a certain spatial location. You wait for a little bit, and then you try to relabel, to basically recall the same water molecules that you've labeled before. Now, why does this work? What is the assumption here? If you label the water molecules at this time point, and they didn't diffuse, they're still there along that certain orientation, then you can cancel out the original labeling that you performed. On the other hand side, if you have labeled some water molecules, they have diffused along a certain orientation, and you try to cancel out exactly the same water molecules that you labeled before, they're not going to be there anymore. They have diffused, right? So you're not going to recover your signal, basically. This is why when we observe actual diffusion, so when diffusion happened, we talk about signal decay, because you cannot recall exactly the same signal that you sampled before, just because the water molecules are not there. That's why you see that the signal from the initial T2 intensity decreases along a certain specific orientation. And another information is that these two gradient encoding are direction dependent, right? So these two gradients will have an XYZ encoding, so that you can say, I'm interested in diffusion along a certain X vector. And at the typical time scale that we use in diffusion MRI, so typically in the order of millisecond, we are capable of using this sequence to, well, probe diffusion in the order of 30 micron, right? So we can use the macroscopy machine to probe diffusion of water molecules at the microscopic scale, right? Which is quite powerful thing to do. There are two main parameters that you want to set at the scanner when you perform a diffusion MRI experiment. And one is the so-called B value that gives you, once again, an idea, like I introduced before, of the diffusion weighting that you have. And this is dependent on the gradient strength and on the diffusion time. So the diffusion time being the longer you're willing to wait for diffusion to happen, and the G, the amplitude, is the amplitude of the diffusion encoding gradients that I described before. And let's say that we keep G constant in this case, and we vary the diffusion time. So once again, you wait longer, the bigger the B value is for diffusion to happen. You see that at the B equal to 0, we go back to our standard T2 weighted image. And the more we increase, the lower the SNR, this signal to noise ratio. So it becomes more tricky to distinguish the tissue boundaries here. But the bigger is the contrast to noise ratio. So the easier it becomes to distinguish between deep white matter areas that show a certain diffusion encoded orientation versus all the other gray matter or CSF areas. And the other parameter that you set up at your scanner during the acquisition is the so-called gradient direction, right? Which can be a three-dimensional vector X. And now we see basically the same example that I gave you at the beginning, but with more information. Now, keeping constant the B value, in this case, so setting a B value of 1,000, now what we do is, given the same axial lines, we start playing with the diffusion encoding orientation. So we start looking for, well, effectively preference of water molecules to diffuse along different axes. And then we have diffusion along X, along a certain diagonal, the opposite diagonal, and along the orientation Z, so the one that comes out of the screen. Right? So if we look at, for example, the two extremes, so diffusion along X, right? So from left to right, versus diffusion along Z, you see that especially this area on the back here completely changes the contrast, right? What this basically means is that if you remember the labeling that I just described before, in these areas, water molecules will tend to preferentially diffuse along X, so that they're not there anymore, and the signal has decayed, right? So we can already say that what happens in this area is that axons are probably oriented along the left-right axis, right? But definitely not along the Z, right? Because here, we get exactly the same signal intensity that we had at the beginning, right? Look at the diagonals here. We have signal dropout for this diagonal, so the axons do a sort of U-turn, and the same thing on the opposite hemisphere, right? But if you look at these two diagonals, then you see that the other part of the corpus callosum is still, well, right, hyperintense, right? So this is exactly the kind of information that we're playing with here. And because specifically of the way that we get this contrast, we talk about an isotropic measurement in white matter. While if you look at, once again, the CSF, so the ventricle areas, is consistently dark across all of the four orientations that we sampled, right? Just because water molecules vary, it's free to diffuse in any possible orientation, right? So the water molecules that I labeled at the beginning are definitely not going to be there anymore. And that's why we talk about free diffusion in that area. how does this translate in practice? So from the signal profile point of view, and from also a typical acquisition point of view, what you typically do when you set up a diffusion MRI experiment is that you, well, effectively acquire some B0 images interspersed into your acquisition, and then you acquire a certain set of diffusion encoding orientation to sample, efficiently sample a three-dimensional Cartesian space. Right? And those are the kind of images that you will get out of the scanner. If you now consider a single voxel, so on the crosshair, on the axial slice on the left-hand side, this is what you're going to get. In respect to fMRI, or to a typical EEG acquisition, on the x-axis you don't have time. So it's not the signal profiles that varies with time, but it's the signal profile that varies with volume. Volume being a different orientation that you're probing diffusion for. The highest peaks, of course, correspond to the signal at B0, so when you're not probing for diffusion, when you switch off the diffusion encoding gradients. And the smaller signal here describes, you give that information about the anisotropy of white matter, of white matter fiber axis at the specific spatial location. If you look at a different area, so in deep white matter in the frontal part of the brain, you see that the signal profile changes. Right? So different spatial location will show different diffusion preferences, different diffusion signal profiles. And given that you're looking either at the ventricle area, so CSF or white matter, also the intensity, also the signal range will dramatically change. And these two changes, these two relative changes in respect to the original signal that you sample at B0 depends on the so-called apparent diffusion coefficient, which we talked about before. So, to give you just a brief summary of what we discussed as a brief diffusion MRI introduction, the images that you acquired, like I said, with a certain gradient encoding will show contrast along the same gradient encoding direction. When actually in that spatial location you have a certain amount of diffusion, the signal is going to be reduced in respect to your baseline. Crucially, in white matter the measures are anisotropic because of the axonal background that we have, and in gray matter and CSF we talk about isotropic diffusion. So moving on to the most basic model that we can use, is there any question about what we just saw so far from the basic diffusion MRI principle, or is it everything? Yeah? All right. So moving on to the basic modeling approach that we have at our disposal to analyze this kind of data that I just described. This is the so-called diffusion tensor imaging, and we're going to see, well, how diffusion behaves in different brain tissues, apparent diffusion coefficient again, specifically the diffusion tensor model, and which measures you can derive from the tensor itself. So diffusion tensor imaging, how does it work? We have our standard set of images. So you've performed your acquisition, you acquire the data from your well-behaved subject, collect the data, and now you want somehow to analyze them, right? We have our B0, we have our diffusion encoded slices, and we set behind the computer and we want to do the initial thing that I showed you before, so estimate the principal diffusion direction, do tractography, and so on and so forth. The basic assumption behind the diffusion tensor model is that diffusion can be described, well, diffusion within all the tissue types that we have can be described with a single bell-shaped Gaussian model, right? But instead of being in the nice environment described by Einstein at the beginning, so a barrier-free environment, we do have, well, we do encounter the barriers, the anatomical barriers that we have inside our brain. And therefore, we should take into account the covariance that comes out of the anisotropic behavior of water molecules. So now, if we want to describe diffusion, we cannot just use a single scalar, so a single number in every voxel, but we need to use something more. We need to use a matrix. We need to use the so-called tensor, right? So that, once again, from a more statistical point of view, we have a three-dimensional Gaussian distribution with, once again, mean zero, so centered, time dependence, and now this capital D becomes in bold, represents the matrix that we're interested in. You fit this model, what you effectively do when you do diffusion tensor imaging is that you effectively fit this model into each and every voxel. Now, this is the basic equation, right? What are the knowns and unknowns in this equation? Well, the most basic one, what you always do when you do modeling, is that you acquire a certain signal and you want to derive the information that are completely unknown to you, right? So on the left-hand side of this equation, you have what you just sampled, which is the signal measured after applying a certain diffusion encoding gradient along direction J, right? So for each and every diffusion orientation that you sample, for every J diffusion direction that you sample, you have a certain signal intensity, right? Which is the profile that I was showing you before. The other thing that we know is that for the same spatial location, is the signal measured without any specific diffusion encoding applied. The other two things that you set behind the scanner, like we said before, is the b-value, so the diffusion sensitivity that you want to give to your acquisition. And then you also know, effectively, the unit vector that represents that diffusion encoding orientation J that we just talked about before, right? So all of these parameters are known to you, by definition, by you sitting behind the scanner and setting it up that way. Now, what you don't know, is the actually 3x3 diffusion tensor. This is what we're trying to estimate here. This is what we're trying to put into each and every spatial location. And what the tensor effectively is, what the capital bold D effectively is a 3x3 symmetric matrix. So, meaning that what you need to estimate are 6 unknown parameters, right? Which are the parameters along the diagonal. So the apparent diffusion coefficient sampled and recovered along direction X, Y, and Z, and the diffusion sensitivity probed along X, but sampled along Y. Now, what that effectively means is that the off-diagonal elements represent the correlation, the covariance of diffusion ampling along different axes. So what happens if I sample for diffusion, I originally sampled for diffusion along the x-axis, but then I listen from a direction perpendicular to it, right? Will I still see some changes, or will I not, right? And of course you can represent those scalars in two-dimensional maps, like we did for all the microstructural parameters before. Now, of course, the crucial question is why do we need to go to this more mathematically sophisticated approach? Why do we need a matrix and it's not enough anymore to just have a single scalar in every voxel? Well, imagine two very simple cases, right? You are in a certain voxel and you can describe diffusion for that diffusion profile using the difference along the x, so the diameter along the x and the diameter along the y, right? Those are going to be, two scalars, right? Now you're in a different voxel, and you have this, right? So there is a clear anisotropy behavior, but you still have exactly the same delta x and exactly the same delta y, right? So if you were just to use the simple scalar, the simple two numbers, it will be impossible to distinguish these two different configurations. And this is exactly why you need to introduce the correlation between the two axes, right? Which you plug into your matrix here. Now what you get once you fit the tensor in every voxel is that you get information about the diffusion coefficient along what is known to be the scanner coordinate axis, right? So your patient is sitting in the scanner, you have a very well-defined Cartesian coordinate system, x, y, z, z being aligned with the bed, with the scanner bed, x left to right, and y anterior to posterior. But what we actually want is that we want to translate this information in scanner axis back to something more useful to us, so to a local coordinate system that that can effectively describe us the principal diffusion direction so that we can start performing the tractography part that we're interested in. And that can be done by, again, applying some math. So we can do what is called to be the diagonalization of the estimated tensor in every voxel, which what it effectively does is that it decomposes the tensor in 3 different eigenvalues and eigenvectors, right? And the eigenvectors are going to be perpendicular to each other, right? And the lambdas, the eigenvalues, will tell you effectively how strong the diffusion is along eigenvector 1, 2, and 3. Now what this means is basically this. Now we're not bound anymore to the scanner coordinate axis, so to the one and only x, y, z system that we had before, but now we have three newly defined axes by the eigenvectors, u1, b2, and b3, which are going to be oriented along the direction of maximum diffusion. Right? So the main eigenvector now, v1, corresponds to the biggest eigenvalue. And now you see what I was describing at the beginning before. If you use this information to sort of compute an equiprobability surface of diffusion, now you can identify easily at least two scenarios, right? An isotropic voxel, so again in CSF, where yes, you have a new system of three-dimensional vectors, but the eigenvalues are roughly the same. So you know that water molecules are free to diffuse in a three-dimensional space. And the second case, which shows clear anisotropy, where one eigenvalue is clearly going to be much bigger than the other two. And, of course, you can apply this now to the whole brain. Right? So we go back to our single-axis slides. We look once again at the three different tissue types, and we have the highest amount of diffusion in CSF, still free diffusion in gray matter, but more restricted. So the radius of the sphere when compared to the CSF is going to be slightly smaller. And then we see clear anisotropy behavior in deep white matter. So once again, cigar shape, meaning that one eigenvalue is going to be much bigger than the other two, and in a local coordinate system, so that we can follow the path of axons at that specific spatial location. Right? Once we have also performed this diagonalization of the tensor matrix, we can estimate the microstructural maps that I was describing before, and the two prototypical, the two most widely used scalar maps that you can get out of a tensor are the fractional anisotropy and the mean diffusivity. Those are the equations, but basically what they say is that mean diffusivity is the average of the eigenvalues, and fractional anisotropy is the eigenvalues variance. So once again, mean diffusivity is roughly how much diffusion on average you have in each and every voxel, and fractional anisotropy is nicely normalized between 0 and 1, and it tells you how sure you are of the estimate of a principal diffusion direction. Right? If you do this for all of the tensors that you estimated across the entire brain, these are the kind of maps that you get. So once again, fractional anisotropy, you're very sure about your principal diffusion direction that you estimate in the hyperintense areas, which corresponds to deep white matter areas typically. Mean diffusivity, of course, is going to be very high. It's going to give you a nice contrast between CSF, gray matter, and white matter, because, of course, white matter is much more free to diffuse in the ventricles. And then axial or radial diffusivity, here called longitudinal, and transverse diffusivity, which is going to show you, which is going to highlight for you different areas of the brain, saying that axial diffusivity is much higher in corpus callosum here in the front, and internal capsule, and axial diffusivity being very high once again in the CSF. How can we translate, now that we have these maps, do they actually mean something? Because once again, always remember, if there's one thing that you should always remember when you do MRI experiment, is they're always indirect measures, right? Like with fMRI, you're not probing neuron spiking. With diffusion MRI, you're not probing axons, right? You're just looking at water molecules. So, but even though we're doing that, can I use those maps to describe about potential pathologies or potential normal development? So if I observe an FA change, a fractional anisotropy change between patients with multiple sclerosis and healthy subjects, what can I effectively say? Does it correspond to myelin breakdown? Does it correspond to axonal breakdown? Does it correspond to, well, any other potential issue that we can have, inflammatory issues that we can have, that our white matter axons can experience? The point is always not to overinterpret the results, right? So there must be a clear-cut hypothesis at the basis before you speculate about what that change might reflect. So we know that if we observe an FA change in multiple sclerosis patient, that is mostly going to be because of myelin loss, right? But it is not a given that in any other case where I observe a deviation from normality of fractional anisotropy will always correspond to axonal breakdown. Especially because the tensor model per se is also insufficient to describe more complicated areas within deep white matter. If you remember what I said at the beginning, is that I said one of the main assumptions of the diffusion tensor model is that diffusion can be modeled as a Gaussian distribution. And one of the things of a Gaussian distribution is that it has only one maximum, right? So what this effectively means is that you're only capable of recovering one principal diffusion direction in each and every voxel. But what happens in two different areas now? So let's take, for example, these are coronal slices now, so we're looking at left, right, inferior, superior direction. Let's look at two different areas within white matter. We look at the so-called body of the corpus callosum here, and we look at the bottom here of the so-called centrum semiovale. Now, why are we looking at these two specific areas? We look at the top one, because there we know that the axons of white matter are connecting the two hemispheres and are going from the left hemisphere to the right through this very narrow path, which is the corpus callosum, right? So that's where you expect that your white matter axons are going to be mostly perfectly aligned, and you're going to be very sure about your estimate of principal diffusion direction. And you're also going to have most likely only one, right? Only one clear diffusion direction. What happens here is that indeed, in the centrum semiovale, you have the callosal fibers coming out of the corpus callosum and fanning to reach the hemisphere, but you also have the corticospinal tract running from all the way down to the pons, all the way down to motor cortex, right? So what you effectively have here are two fiber populations that cross each other at 90 degrees. And now what happens to your tensor here? It gets completely confused, right? I can only give you one direction, but here there are two. So the only thing that I can tell you is that I'm going to collapse into a pancake, because I can sense, I can see that there are two orientations crossing at 90 degrees, but I cannot tell you whether they're like this, or in any other possible configuration on the plane, right? So what this effectively translates into your nice microstructural fractional isotropy map is that if you compare these two areas, we're still in white matter, but they show different intensities, right? It's very intense here in the corpus callosum and big loss in the centrum semiovale. But it doesn't mean that the brain is not as it should be, right? It doesn't indicate any pathological phenomenon. It's just because of the limitation of the model itself that we see this difference in contrast. Once we have estimated the principal diffusion direction, so going back from the microstructure that we discussed so far, we can translate these into the, well, some images that you probably have seen already, which is given the principal diffusion direction that we estimate, right? So the x, y, z, the three-dimensional vector, the red vectors that we have estimated from our tensor after the diagonalization, we can color code them by equating x, y, z to the RGB color scale, right? So x corresponds to red, y corresponds to green, and z corresponds to blue. If you look here at the color coding map, you see that, once again, in this area of the corpus callosum, they're bright red. So axons mostly oriented along the left eye, right orientation. Blue is coming out of the screen. So like in this case here is the corticospinal tract, and green being mainly oriented in the anterior-posterior direction, right? So just by looking at this color-coded map, you already have a lot of information about the anatomical path that you've sampled from your brain. So that if you look at one of the classical anatomical textbooks describing white matter paths, so white matter connectivity, white matter tracts, you can start singling out different long-range pathways. So again, we have a corpus callosum here, and we can identify it with this red color, with the cingulate fibers, so these two dots here, and you find them in green, so easily distinguishable between the blue and the red color, and so on and so forth for all the other pathways that you have there. So we're still not doing the three-dimensional virtual dissection that I talked about before, but just by looking at these color-coded maps, we can distinguish the different axonal projections that we have in the brain. Now, moving on from the modeling that I just described before, so moving on from or moving backwards, if you actually want, from the diffusion tensor model that I just described before. What about distortion correction for diffusion MRI? So unfortunately, the images from the scanner don't come out of the scanner completely clean. They don't come out very nicely, already smooth and ready to be analyzed. But you need some preprocessing in order to be able to use these data. There are several distortions that can happen because of noise and other phenomena. And the two main ones that we observe when we do EPI acquisitions, so not just diffusion but any echoplanar imaging acquisition, are the so-called susceptibility-induced distortions and the eddy current-induced distortions. Now, what are these? So how do these translate in the images that we actually observe coming out of the scanner? So what are the susceptibility-induced distortion? Susceptibility-induced distortion means that you paid several million euros to buy your MRI scanner. You have been granted that it's a 3T, 7T, 9.4T, you name it. The moment in which you put an object into it, the field gets completely distorted, right? So what you paid for is not there anymore. Just by therefore we put a phantom or a human brain, which is what we're interested in now, and the field that we got sold is not exactly the same anymore. This translates in our machine expecting a certain field, but receiving information about a completely different one. And this effectively translates into the so-called susceptibility-induced distortions which we observe here. So you see that in image C, it's as if somebody removed the frontal part of the brain and stretched it backwards. While if we change what is known to be the phase encoding directions, which we're not going to discuss here, but it's again a sequence parameter that you can set on the scanner, the distortions basically go in exactly the opposite direction. It's as if somebody removed or cut off the back part of the brain and stretched the brain all the way towards the anterior position. Another story is the one related to the eddy current-induced distortion. These are basically spurious currents that go around your big magnet. Just because you're stressing the system, so you're applying so much energy in such a very short amount of time, you elicit these eddy currents, which basically sort of get, again, a misreading from your, effectively recording coils. And these again translate into a difference from what the machine is actually expecting. So in a normal scenario of a subject which is lying very still in the scanner, what you observe is that it looks as if the subject is moving, right? But this is not just motion. This is also some non-linear stretches around the edges of the brain, right? So it's not even consistent between the different volumes that you acquire. And these eddy currents are actually dependent on the diffusion orientation that you're sampling in that volume, right? So these two things are something that you observe in your raw data that actually shouldn't be there. And now if you run all of your fancy model or your fancy math on top of it, this is basically going to give you a wrong answer. Just because if you want to analyze this voxel consistently along your acquisition, this voxel is not going to be the same along your 4-dimensional data. It will move, right? So you need to find a way to hold that voxel still and to just retain the diffusion encoding information that you sampled at the beginning. And there are two tools into FSL, which is the software that we develop in Oxford at FIMRI, which are called Eddy and Top-Up, that are being developed by Jesper Andersen. And these are the two main tools that allow you to correct in one simple go all of these distortions that I just talked about before. What Top-Up does is that it estimates the so-called off-resonance field. So this has to do this has to deal with the fact of that you have susceptibility-induced distortion in your data. So what the tool tries to do is that it tries to map effectively the field, that's why it's called the field map, effectively the field that you should have, that should be homogeneous if there wasn't anything inside your scanner, but it tries to map that field once you insert an object, a phantom or a human brain, inside the scanner itself. And you see here that, like I said before, it's not that you have an homogeneous field along the entire, well, across the entire volume of the brain, but you do have differences highlighted by the hyper-intense and darker regions, like it's shown here. Now, why is this field map useful? Because we can actually translate into a displacement, into a voxel displacement map. So that information of the changes across the field map can correspond, can give you information of how much and along which orientation that spatial location has moved because of its susceptibility-induced distortions. So that you can see that we can use the acquisition that we have originally performed, so along, once again, the two different phase encoding directions, which are once again parameters that you set at the scanner, like in this case along the anterior-posterior axis and posterior-anterior axis. So if you look at the two axis slices, you see the distortions that I was describing before. And given these differences, you can infer the field map. If you now use this field map to correct your data, you see that the geometry of the brain has been restored. So it's not stretched along any orientation, but it's actually the brain as it should look like given any other anatomical acquisition. The second tool that is available in FSL, do you have a question? Sure.
Yeah, sorry.
Of course.
Is it possible to compare this map with the field maps that are also acquired in fMRI?
Sure.
Like, basically it's similar, the concept is...
It's similar, but not, well, what you do when you acquire a field map is that you perform a different acquisition itself, right? What you do here is that you acquire, effectively complementary information from which you derive a field map. So you actually, it has been shown that it is a much more robust estimate of a field map than the one that you obtain when you do a bespoke field map mapping. So you can use it also for fMRI data. Yeah?
In the African tortoise universe, you basically scan it twice with whole diffusion in two directions.
Yeah.
And with the top up, you don't need to do that one.
No, because you just need, what you effectively need is that at the most basic level, you need two different B0s, so two different diffusion unweighted bodies with a different phase encoding orientation. So that's all that you need to map the field map. You want, if you're in a very luxurious scenario in which you have unlimited time, a very well-behaved subject, that's where you would scan the whole thing twice. Because now, yes, you can estimate the field map, but you also have a square root of 2-factor in gain in SNR, just because you're repeating the same acquisition twice.
So it's just another.
Exactly. So you're boosting your SNR effectively. Any other questions? Cool. So the second tool that I'm going to briefly discuss today is the EDDI tool, which is the tool that allows us to to effectively perform the correction, the pre-processing of the data on the full 4-dimensional data set that we've acquired. Meaning that this tool can correct for susceptibility-induced distortion, so it uses information coming from top-up, namely the field map that we estimated. It can correct for the eddy current effects that I discussed about before, but it also can correct for motion, right? Because any subject at a certain point across a 1-hour typical acquisition or less will start feeling restless in the scanner, right? And you need to account for that. So how does EDDI briefly work? You have acquired your data set here, which comprises, well, here just one simple axial example, but once again with different diffusion encoding orientations. And given this initial scan, which will have, which will have all the distortions that we discussed so far, we have an initial estimate of our field map, eddy current field, and motion parameters. We apply these distortion information to our raw data set, and we basically get a distortion-free, if you want, image for that certain diffusion encoding orientation. What you do with this is that you give it to Zolter, the prediction maker, so that Zolter can learn how the prototypical data set, how the perfectly corrected data set should look like, right? So what effectively Zolter does is that now, given a p-value and a diffusion encoding orientation, it can get you out a prediction, right? So Zolter tells me how the brain of that person in that spatial location for diffusion encoding orientation 100 should look like, right? Bam, and you get out a prediction. What you do with that prediction is that you invert the transform that you've estimated at the beginning, so that you go back to the effectively distorted space. And what you can do now is that you can compare your estimate, well, your prediction, with the actual data set that you've acquired, right? You compare them, and what you can do is that given the, well, effectively the residuals from your distorted prediction and the data set that you acquire, you can update, you can locally update the parameters that you have here. And then you repeat the process again, right? With updated the parameters, follow the same path until convergence, right? So until here, until this map will be completely, well, smooth, zero everywhere, right? Meaning that the distortion parameters that you've estimated are so good that now you can bring exactly the prediction back to the raw distorted space. And remember this prediction thing, because this is also a very powerful feature that is present in Eddy. And to give you like a bit more detail, what is under the hood of Zolter, so what does actually Zolter do? It is a machine learning approach. It is the so-called Gaussian process machine learning approach. And what it actually does is that it builds, given the red data points, which are the signal intensity at a certain voxel that you have sampled in a three-dimensional Cartesian space, it basically fits a surface, a representation of a signal for you. So then now you've estimated the surface, and given the surface, you're capable of estimating any signal intensity for any given diffusion encoding orientation, right? So this is where the prediction that I discussed about before come out. And we can do this, of course, for multi-shell prediction. So in the case where we have acquired multiple B values within the same acquisition, and we see that we get two complete different prediction if we were to apply the simple tensor model rather than the more complex Gaussian process approach that I just described before in the scenario where you have fiber crossings, with our tensor giving us the non-informative, but basically wrong pancake shape that I discussed before, and the Gaussian process giving us the more complete fiber crossing scenario, which is actually the underlying truth. How does it perform? What happens when we apply the Eddy and top-up tools to our data? Here we show an example for the Human Connectome project data sets where we acquire 150 direction with a pretty high B value of 3000, and using the blip up, blip down, so the two different phase encoding directions to estimate the distortion. This is relieving this distortion. On the left-hand side, you have raw data, and on the right-hand side, you have corrected data. So you see that on the right-hand side, especially at the top, brain is squiggling quite a lot. On the right-hand side, it's perfectly corrected. And the only thing that you notice is the diffusion contrast that change across your entire acquisition. It works also pretty well for in even more extreme scenarios, so for a very high B value of 1000, where it becomes pretty tricky to see, again, the brain. But if we zoom here, and if you like sort of squint your eyes in these areas, so where you have one of the brain gyrate, one of the main brain cell sites, you see that these jumps all over the place, while here the U shape of the sulcus is quite stable. You don't just have motion that happens across the different volumes, but you might have some specific subjects that move while you're acquiring that specific volume. So you don't just need to account for the head motion between the volumes, but you also need to account for the brain motion happening within the same volume. And what this practically means is that you start your acquisition, you start acquiring that volume, and the subject is perfectly still, so reference scan, and then your subject starts moving, right? Second slice, third slice, fourth slice, and so on and so forth. So what this means is that even within the same volume, the slices will not be aligned with each other, right? You're going to have a stack of slices which is going to be completely misaligned along the x-axis, along the z-axis, sorry. In brief, what you can think of is you start acquiring from the bottom, and you start acquiring your axial slices, right? So the green shaded area here. All of a sudden, inside again the same volume, your subject looks up, right? Scanner doesn't know that, so it keeps acquiring the slices along what it is for the scanner, the same orientation, but effectively what you're sampling now are these slices, which practically means that you've sampled once the green shaded areas, you sampled twice, so the scanner has seen twice the yellow shaded areas, but it has never seen the red area, right? So that is information that is lost. But that is information that you can actually recover using the predictions of the AD model that I just discussed before. So thanks to the Gaussian process, we can learn the signal representation even in that area that we're missing for this specific volume. And if you do that, here is one example of an old subject which has moved quite a lot in this volume. You see that, again, on the left-hand side, slices are not nicely stacked with each other, and with the correction that we've recently implemented in AD, the slices are perfectly aligned when it flickers, right? So, once again, the brain geometry has been restored. Now, why is this, in which scenarios, this intra-volume motion is particularly interesting? Well, we mostly needed that for the project that I was involved in when I was in Oxford, which is the so-called baby connectome, or the Developing Human Connectome project, in which basically we were set to scan 1,500 well-characterized fetuses and newborns, multimodal acquisition, so diffusion, fMRI, and anatomical information. We built all the analysis pipelines, we developed novel acquisition techniques, but we have to deal with motion, right? Guys are never not going to lie still, even if you tell them. I'm not gonna discuss the fetal scenario, which is even more complicated. But what we did for the neonates is that you scan them when they're fast asleep, right? So there's been developed a pillow that sort of hugs them, so it helps them to fall asleep. Put them in the scanner, and you start scanning them. What of course can happen to the babies, to the neonates, is that they can wake up, start crying, so a lot of motion happening, but they can also be dreaming inside the scanner, right? And again, dream might correspond to quite a lot of motion. And thanks to the tool that we have available in FSL, while typically, people that are interested in development and acquiring neonatal data usually threw away 80% of their data set on average, we're basically able to recover almost 100% of all the data that we acquire. So once again, talking about the susceptibility-induced distortion, left-hand side is the raw neonatal data, right-hand side is the corrected volume. And when it comes, of course, to motion distortion, left-hand side is again the raw data with the susceptibility distortion, with the baby moving around. And on the right-hand side, distortion and motion are gone, and you just get the diffusion contrast. Any questions about this? Yes. Probably you would probably help. Yes. Anyway, to move to the very last part of this, first hour and a bit more, automated quality control. Right now that we discussed about the pre-processing of a data set, it's becoming more and more common to acquire big data sets. Right. So what I'm showing you here is across the lifespan a certain brain developmental phenomenon, which can be cortical thickness change, brain volume change, you basically name it. These brain feature change across the lifespan, and what are actually available to the scientific community, starting from the Human Connectome project, is, well, effectively big MRI data set. So it all started from the Human Connectome project, 1,200 subjects scanned between 20 and 30-year-old. In the UK now, what we have going on is the UK Biobank, where it's set to scan 100,000 individuals, fully profiled, genetic, clinical, and behavioral information and MRI data set. In the US, we have a new HCP lifespan also starting, so 3,000 subjects being scanned across the entire lifespan. And then, of course, what I just described, which is the project which I was involved in, the UK developing Human Connectome project, which is very interesting, of course, because they're all very interesting, but especially the DHCP has the highest rate of change in the shortest amount of time. You really see the babies changing gerification from 1 week to another, so not through years, but from 1 week to another. And if you think about having this quantity of data, you going through each and every single volume, each and every single subject to check, is this volume good, is it bad, can I keep this subject, can I keep this one? It's impossible. That would take a lifetime, basically. So what we also developed is in FSL is the so-called EDDI quality control tool, which, given all of the things that EDDI can correct for, so all the parameters that it can estimate, we can use these parameters, well, we can derive extra quantities from these estimated parameters to obtain quality metrics. So quality metrics about our data set. And just to summarize, this can correspond to motion information, motion quality metrics, so between volume, and within slice itself. We have quality control, quality metrics regarding distortion, so susceptibility and eddy induced, but we also have summary measures like the CNR and contrast to noise ratio that was discussed at the very beginning. We have developed two different tools, which are called Quad and Squad, so quality assurance for diffusion MRI dataset and study-wise quality assurance for diffusion MRI dataset. And the way that it works is that Quad performs so collected quality control information for each and every single subject that is stored in a JSON database for all the individuals, which is then read by Squad, so by the group-wise tool that we have, to create a report, so quality control group report, visual report, and a quality control database for the entire cohort. So that once you have this database, you can either put your original subject into the context of that database to decide whether a subject is performing well or bad, or you can use this information on your own study. So how good is my acquisition compared to the Human Connectome Project one, the UK Biobank one, and so on and so forth. And this is how the visual report will look like. So you do have a single subject report here. On the first page, you're given some averages about all the quality metrics that you have computed. And given the power of the quad-squad combination, you can now report those quality metrics in only on B0, so diffusion unweighted volumes, and of course, given some deviation from the average value, for example, of a cohort, we can identify problematic subjects, like in this case, where not all of the distortion, well, not all the artifacts were correctly pre-processed. But we also can estimate, for the first time actually, this is the only tool that can estimate, that can quantify the angular contrast to noise ratio, right? So how much directional angular information you have in your data set. Meaning that the higher the quantity is, the lower the uncertainty that you get out of bedpost-X, which is the tool that we're going to discuss after the break, you have, right? So how better your estimate of the axonal orientation is going to be, given the CNR measure. And of course you can use, like in this example, like we did once again for the baby connectome, to quickly identify very good subjects, average subjects, and subjects for which, well, that have moved a lot, and that show a lot of distortion and residual artifacts. Right. So I would do a quick break here, 5 minutes or so, unless there are some burning questions. Cool. 5 minutes? È troppo? Vabbè,
No, no, ma guarda, io avevo già...
So the one before the break was the easy part. Now we're going to the slightly more modeling part. But actually, that's going to be this is going to be the more. Yeah, I'm losing my voice already. So sorry. So now we're going to see basically the part about diffusion tractography and advanced fiber modeling estimation. So that hopefully once you go back to your family and friends, you can impress them by creating these very fancy movies of, well, their own brain or somebody else's brain to show their white matter architecture at these unprecedented details, right? So this is a technique known as track density imaging, and we'll see later how actually you can get to these images given your, well, even very basic, very standard diffusion data sets that you can analyze using in vivo virtual dissection using tractography. So you see that basically what is passing through here, this is a movie created by Sajib Abdi in Oxford, and what we're showing you here is that at the resolution of 200 microns, so sub-millimeter resolution, you can start seeing the white matter fibers projecting coming out of a corpus callosum, for example, right? So you do super resolution starting from your acquisition, which was done at millimeter base resolution. We're going to talk about this a little bit later. Where we're going to start now is talking about advanced estimation of how you can estimate fiber orientation, so moving beyond the tensor that we described at the beginning. Then we're going to go to describe probabilistic tractography that we have also available. These are the two tools that we have available in FSL, so bedpost-X and PropTrack-X, doing the two respective parts. And then, if we have time, we're just going to go through some tractography applications examples. Now, to start, let's go back like a very small single slide recap of what we can do with a diffusion tensor model. Basically, we can get pictures like this, right? So we can fit into each and every voxel our nice tensor. We can derive the principal diffusion direction using the diagonalization that I described before. And based on the assumption, once again, that water molecules diffusion correspond to axonal orientation, we can fit those kind of images, and we can use them to do tractography. But does this assumption, well, I'll give you a spoiler already, but does this assumption work everywhere in the brain? So if we look at these two, well, post-mortem dissected brain and consider, well, two prototypical voxels in two different spatial locations, we see that in these, can you see this? Yeah. So this voxel mainly shows only one fiber component, so the fibers coming from the corticospinal tract and projecting all the way to motor cortex, let's say. So you have one densely packed bundle of axon nicely and coherently following the inferior to superior direction, so along the z-axis. If we take another voxel, like here, you see that now we start having intersections of two different fiber populations, right? Fiber population projecting to the superior gyrus there, and the fibers of the so-called superior longitudinal fasciculus following, well, the Y orientation, right? So to the anterior, to the posterior part of the brain. So what we have actually is that given our resolution, given our millimeter resolution, we have to find a way to deal with these complex subvoxel fiber configurations, right? So to understand, like, once again, to go back to the modeling perspective, which is what we ultimately want to do, is let's take some typical example. Let's try and model some typical examples of fiber configurations that we can find anywhere in a typical brain. So let's start from the easy bit. Let's start from a voxel in which you have only one clear fiber population following the orientation along the black stick, right? So this is what we're going to fit into that voxel. If we want to look at the three-dimensional signal profile that we have acquired from our scanner, what we are going to expect, what the simulation gives back at us, is that donut-like shape. If you remember what I said at the beginning, what that donut-like shape tells us, what it's showing us, is that you have the highest amount of signal loss, of signal decay, along the black stick. So you're losing most of the signal along the orientation of the black stick itself, right? Which in a scenario one fiber population, that's exactly what you expect, right? Water molecules diffuse, you lose signal. And that is the only orientation that you have. Therefore, if we fit our diffusion tensor in that voxel and we use our, well, estimated diffusion tensor estimate to predict the signal. So I go back to my original equation. I have estimated D, and now I can derive S, the intensity of a signal, and I plot it, and I reconstruct the three-dimensional shape of it. They nicely correspond, right? So reality, the measured signal, nicely correspond to what I'm able to predict, meaning that my model fit is pretty good, right? Tensor is giving me a good result. If I look at the DTI ellipsoid, so after diagonalization, we have clear anisotropy, cigar shape, right? One principal diffusion direction. If we now take a cross-section, so a plane along the XY orientation, and we look at the prediction, so this guy over here at the red surface, and we start putting the intensity, the measured intensity that are discrete, of course, because you only sample a certain number of volume on top of the surface, they nicely fall on top of that, of this specific cross-section, right? So once again, nice confirmation that our model is giving good results. Let's now complicate the scenario a little bit more, right? Let's now consider a different voxel in which you have two fiber crossings at, let's say, exactly 90 degrees, so on a plane, right? Already here, if you look at what you're actually measuring, so at the measured signal profile there, you see that if before you were immediately able to, well, predict that the axons were running along a certain orientation, the scenario changes here, right? Because actually here you have the highest amount of signal decay, not along any of the two orientation, but you actually have it along the diagonal, right? As if it's telling you, I have only one fiber population that cuts through these two equally prominent fiber populations, right? So you fit the tensor once again. Tensor gives you also a completely different shape from the measure that you have. The DTI ellipsoid collapses to, well, the pancake shape that I was describing you before. So tensor desperately, well, can only estimate one direction, but it tries to tell you that there are actually two, but it can tell you exactly which one are those, so it only gives you the plane. And once again, if we take a cross-section here, we see that the prediction along this cross-section is circular, and the measurements don't fall anymore on the predicted signal shape that you have. Now you got the rationale of these. We complicate the things even more. We have three fiber crossing at 90 degrees into a different voxel. Measure signal shape completely doesn't give you any information anymore about the signal decay, any meaningful signal decay from which you can immediately infer the axonal orientation. You fit the tensor. The estimate, the predicted signal shape that you get out of the tensor is a sphere. So tensor gets completely confused here. DTI ellipsoid is a sphere, which, if you remember, is the shape that we typically get into CSF, while here we are simulating white matter voxels. And once again, taking the cross-section and overlaying the measurements, we do get a bad fit. So how can we, try to put those three different shapes into the context of a brain? We take here another cross-section, well, one of the same cross-section that I showed you before. We look at the three different areas, so taking the simple one, the body of the corpus callosum, very good fit, very good prediction of our tensor shape, so cigar shape right here, very clear anisotropic behavior. We go here at the bottom, at the level of the pons, where you have the corticospinal tract fibers running from the bottom to the top of the brain, but you also have what they're called the transpontine fibers running along the left to right orientation, so two fiber crossing at 90 degrees, on which the tensor shape collapses into a pancake. And then in the central semiovale, where you once again have the callosal fiber coming from here, corticospinal fiber running from here, and the superior longitudinal fasciculus coming out of the screen, so three fiber components crossing at 90 degrees, again, tensor collapses into a sphere, right? So what you actually can say from these two different scenarios is that the principal diffusion direction that you estimate is basically meaningless, right? Can't use it to do, well, basically tractography. And even the FA map here will show variations in intensity which shouldn't be taken for, well, effectively deviation from normality from a healthy brain. Moreover, what you also have when you do this sort of modeling approaches is that and this is a crucial thing that's going to come back over and over in this part of the talk, is that once you estimate your principal diffusion direction, you have a certain degree of uncertainty about it, right? So that is kind of reflected by the fractional isotopy measure that we saw so far. And this uncertainty actually comes from two sources. It comes from the noise, natural noise that you get in any acquisition, right? Given by the scanner signal profile, the day that you scan your subject, eddy currents, you name it. But you also have the modeling errors, right? Because, as it usually said, all models are wrong, but some of them are useful. That is definitely the case for the diffusion tensor model, but it also introduces some noise just because of this imperfection of the model itself, right? How can we translate visually the uncertainty in our estimate? So if we look at these maps, these are maps of the so-called uncertainty cone. And if we look at this area, or at these two different areas in the brain, once again in the axial slice, we see that the uncertainty cone is very small. It's almost imperceptible in the corpus callosum once again. So again, densely, tightly packed white matter axons. But at the moment in which we reach an intersection of two fiber population and we use the diffusion tensor model, you see that the uncertainty cone kind of explodes. Well, it becomes significantly bigger. It definitely explodes in the CSF areas, right? Where you definitely are not sure that the principal diffusion direction estimated is actually meaningful. And if we zoom a little bit more here, you see that this cone basically becomes significantly bigger once these two fiber population cross with each other. And luckily, we're not just limited to use the diffusion tensor model, which is still very useful, as we're going to see later in the talk, but especially when we're interested in doing in vivo virtual dissection. So if we're interested in tractography, we can use more advanced models. And one of these is the so-called ball and stick model, which is what the bedpost sticks toolbox uses to estimate fiber orientation in FSL. And what this basically is from, the mere mathematical modeling point of view, is that it's an extension of the original exponential equation that we had at the very beginning. So if you remember it, that's basically what we had at the very beginning. So we still try to model the measure signal for the gradient orientation. We have the exponential of the b value and the orientation x. And now you see that we have two exponential. So we're trying of distinguishing two different compartments of water molecules. We're trying to describe an isotropic compartment, so the ball, so the water molecule's fraction that is free to move at that specific spatial location. And we try to combine it with the exponential, with the compartment. This is why we call it a multi-compartment model. We try to model the purely anisotropic, so the stick volume fraction, right? And that's why the first exponential doesn't have any dependence on the unit vector that represents your diffusion encoding orientation, but it only has a dependence on the b value and on the d, on the diffusion coefficient, while we introduce the dependence, the orientation dependence, in the anisotropic compartment, right? And we do weight these things by f, which is the so-called anisotropic volume fraction. And basically it measures how much of a signal is explained by the anisotropic compartment in comparison to the isotropic compartment, right? So is the signal in that voxel mostly dominated by free water, or is it mostly dominated by anisotropic behavior of water molecules? And effectively what we try to estimate when we do this model is once again the anisotropic volume fraction f, the diffusivity, so not the tensor anymore, but just a scalar in this case, and the fiber orientation, the red V here, right? So these are the parameters that we want to get out. So not just the tensor anymore, but these are the parameters that we tried to get out from this model. And the nice thing, the ball and stick model, is that you can kind of immediately see that it's very easy to expand, because now we're not limited to have only one stick, so one clearly anisotropic compartment, but we can have multiple of them. So rather than having only one volume fraction, we have a summation of n volume fraction, right? N being a number from, well, typically 1 to a maximum of 3, being 1 to 3 fiber populations that you're capable of fitting into that voxel. So once again, get the measure signal, B value, and what you're trying to estimate are effectively the red letters, the red quantities there. And if we go back to our simulations and we compare how well we're doing with the diffusion tensor model compared to the effectively ball and multiple sticks model, we see that in the more complex scenarios of a 2-fiber orientation and 3-fiber orientation crossing at 90 degrees, you get, well, a very bad fit between the predicted signal and the measure signal if you were to use your DTI model. But if you now use this equation and you try to predict S, so the signal that you measured, you actually get a very good fit between the prediction, so the red surface, and the measured blue dots that you get out of your scanner. So it is already quite a gain in terms of signal representation, goodness of fit, in respect to the diffusion tensor model. Now here it is, the uncertainty concept comes back, and I was going to see in a second why. This is just if you were to, well, try to estimate some fMRI quantities, and you were interested, sorry, should I check these transitions? And you were interested in estimating the uncertainty about the beta values typically that you estimate in fMRI. That's very easy to do. There is an analytic formula to do that when you do simple linear regression. So when you apply the so-called general linear model, which is what the typical basic analysis of fMRI data allows you to do. You don't have that kind of, well, luxury when you want to apply this kind of modeling approach that I just described for diffusion MRI data. You don't have just the GLN, but you need to use a slightly more advanced framework to estimate the variables that we're interested in. And in the case of bedpost sticks, what we do is that we use a so-called Bayesian probabilistic framework to get the interesting quantities out of it, which basically means that we have our data sets, we have our generative model. What the generative model effectively is the equation that I just showed you before. So you have a way of modeling your signal, and you can also account for noise. And by performing Bayesian inversion, so a probabilistic inversion, let's forget about the details here for now, but keep in mind that it is a probabilistic framework, so it's not a simple computing the fraction or an analytic formula to estimate this. What you can get out of this is a whole distribution about the parameters of interest that you have in your model. So it's not just that in every voxel you now have one number for D, but you're actually going to have a distribution of likely values that D can have in a specific voxel, right? If you were to use this, once again we're here, if you were to use this framework. So we can have the so-called posterior distribution of our parameters of interest. And what having the distribution basically gives you is that it's not just a single value, it's not just the average value of the expected value that you're going to get for that parameter, but you also, given the standard deviation of this normal distribution, you can also have the estimate of how certain you are about that parameter value, right? For all of the parameters that we have there. So what effectively means is that we don't need to rescan the single subject 100 times to quantify the uncertainty, but we can do that for a single data set. And if we now look at two different voxels, one in deep white matter like in the body of the corpus callosum, and one in gray matter or CSF, we see that our sticks, our anisotropic compartments, will show a very low degree of uncertainty. So you're very sure that water molecules will tend to diffuse along that orientation, while this uncertainty will basically explode in a gray matter CSF voxel, right? Just because water is basically free to move everywhere it pleases around in that specific spatial location. And once again, if you were to break this down into the ball and stick model that I presented before, so the multi-compartment model, you will have effectively a distribution of isotropic compartments of the balls and a distribution of sticks of anisotropic compartments. right? And if you were just to collapse them on top of each other, what you basically have is the representation of the uncertainty of a diffusion direction, but of the diffusion, principal diffusion direction that you estimated in that voxel. Of course, now the question becomes, how do you select? Because what the user does when anybody uses bedpost sticks is that it specifies how many fibers you basically try to estimate in every voxel, and you typically set that number to 3. But now, is there a way to actually let the algorithm decide whether in one voxel you should have 1, 2, or 3 fiber compartments? And we can embed that into the Bayesian framework that I just presented. It's basically, sorry, comes down to using a different prior, which is called the automatic relevance determination prior, but basically automatically determines the most likely number of fibers that you have in each voxel. And the basic way that it works is that once again it does this comparison between actual sample data and predicted data that you have. So we are in a certain voxel, our diffusion profile looks like that, so all the signal goes up and down depending on the diffusion anisotropy behavior. And if we model this signal with 1 or 2 stick, so we're able to predict the signal following the blue line, we don't have any significant gain between the two different modeling approaches, right? While if we're here in more complex voxels in which, for example, 2 fiber crosses, we see that modeling just using 1 stick doesn't do enough of a good job as modeling the same voxel using 2 sticks, right? So the prior basically automatically decides that yes, in this voxel you should retain the 2 fiber information, while here you should basically bring the anisotropic volume fraction of a second fiber to effectively 0, right? And this is automatically done by the Bayesian framework that you've set up in bedpost sticks. What do you get out of the analysis? You basically get the estimated orientation of the fiber population for the 3 different sticks, so the independent ones, and you also get the anisotropic volume fractions that have been rescaled by this automatic relevance determination prior, right? So that if you were now to threshold the volume fraction for, let's say, 5% of explained signal, you see that only very few free fiber crossing population will survive that threshold. So effectively what you do when you do bedpost sticks is that you are going to fit 3 fibers, but the anisotropic volume fraction is going to be brought all the way back to 0, so that you can effectively threshold it and only retain the useful information. And if you were to zoom on the usual suspect area, so once again the centrum semiovale, you see that in this case we have the callosal fibers coming out of the body of the corpus callosum and fanning to reach the contralateral cortex, but we also have the corticospinal fibers in blue, and well, roughly you can see the 3rd fiber component in green of a superior longitudinal fasciculus. Yes?
Even if you set the ARD to 4, it wouldn't matter. Most of the time you'll just consider it relevant. It takes a
You mean in the toolbox when you use the well, that's a different thing. You can set it between 0 and 1, and it actually tells you how dominant the ARD should be.
So if you're modeling for 3 fibers,
Mm-hmm.
I think that's the new quadrant.
Mm-hmm.
So suppose you change that to 4.
Mm-hmm.
It's going to zero out all that anyway, most of the time.
Probably yes, but just because typically you don't have a kind of angular information. You don't have enough angular information to model like more than 3 fiber components. At least I've never seen it, but yeah. But in that case, again, VRD will kill the 4 fiber component by definition. Yeah. But it's not that it's doing it automatically because you set out 4, but just because you don't have enough information in your signal to represent the 4 fiber population. Yes.
In the dashboard, it's the default parameter is 3, like the
For, yeah.
population. Do you think that it's enough for you to just see the complex of the white matter crossing fiber?
Let's again, that's typically the maximum you can do anyway.
It's enough?
Whether it's so rather rather than including more fiber components, what you usually can do is expand your model and start to introduce like concepts like fiber dispersion and these kind of things to try and model like fiber fannings and these kind of things. So estimating more than 3 unique fiber compartments is tricky. Yes.
From a model perspective, can you please explain what is the difference between the ball and stick model and other models such as constraint, spherical interpolation, spherical harmonics?
Sure. We can discuss about this a bit more in detail later if you want, but to give you like an idea of the differences, what effectively the ball and stick is a spherical deconvolution approach, right? Because you do have a kernel which is via anisotropic, which is the stick model effectively. The main difference between this spherical deconvolution that is done in bedpost sticks and the constrained spherical deconvolution approach based on a spherical harmonics basis typically is that the bedpost sticks approach is the so-called parametric approach, and the constrained spherical deconvolution is the non-parametric approach, right? So that is basically the main difference, is how you get down to the estimate of the parameters given these two different models. Given that the parametric approach, bedpost clearly defines some, well, let's say, even though they're not microstructurally relevant, but some, let's say, microstructurally relevant parameters, diffusivity, fiber orientation, and so on and so forth, while for constrained spherical deconvolution, you have a spherical harmonics, which forms an orthonormal basis on the surface of a sphere, right? So effectively what you're trying to do is, given a basis, you just try to fit the coefficients of that basis. You just try to estimate the coefficients of that basis, right? Yeah, but that's a very, very good question, actually. Anything else? Yes?
And the two approaches will be equivalent if there were only 3 fibers.
And hopefully they should be equivalent. The only thing is that typically with constrained spherical deconvolution, you're going to estimate a surface, while with bedpost, you will have 3 clearly defined fiber populations.
But you also have the variance, the uncertainty.
You're, exactly. Plus with bedpost,
Also like a surface.
exactly. Plus with bedpost, you're going to have the uncertainty. Ultimately, it is going to be a surface, but it's not parameterized as a surface, right? Yeah. And if you do like the most basic comparison to compare the diffusion tensor approach and the ball and stick approach, you see of course the increased wealth of information that the ball and stick model gives you. So saying that basically the principal diffusion direction that you estimate out of a diffusion tensor should roughly correspond to the orientation of the first stick, so in red here in the ball and stick model, but then of course you lose the information, or actually you get completely, well, almost meaningless, let's say, information out of a DTI model in fiber, in regions where fiber tend to cross, while you actually reconstruct the crossing correctly using the more advanced model. And how can you be sure that actually, well, all this modeling is meaningful? Well, one way to ensure yourself that what you're actually, the fiber populations that you're estimating are meaningful is that they should show a certain degree of spatial coherence, right? So once again, if you start from a location and you try connect the dots, those fiber populations should nicely be aligned along the path of the fiber itself, right? So all the reds are roughly in line, they're continuous in space, and the blue ones as well. Right, so this was about advanced fiber modeling. So if you don't have any question, now we can move to the Proctor kicks, so to the probabilistic tractography. How do we perform probabilistic tractography, at least in FSI, using the Proctor kicks toolbox? And first of all, well, price of why we should be interested, why we should be doing structural connectivity studies, so estimate the structural connectivity profile of the brain. And that can be, once again, because we're interested in certain diseases. So for example, in this nice representation by Catani done in the paper in 2005 shows you that depending on which white matter connection is interrupted, these can give rise to different language deficits, in this case, like apraxia or aphasia and so on and so forth. So given the disconnection between two brain areas, you can elicit different pathologies. So that's why you might actually want to probe the white matter connectivity in vivo. You can do longitudinal studies or cross-sectional studies at the single white matter fascicle level and combine the structural connectivity information with the microstructure information. So looking at the track-specific developmental microstructural profile and see how it changes, how actually it becomes different from track to track inside the brain and how it changes across the human lifespan. And of course, another thing is that you might be interested in comparative studies between human and macaque, for example, and try to define homologous region between the two species, or just like in this example, define two different areas, like in this case F3 and F5 in the macaque cortex, try to define two different areas based on their structural connectivity fingerprint, right? So two pieces of cortex within the same animal will show different projections, different upframe projections. And if you want, you can basically now cluster these two areas based on their structural connectivity profile, right? So you can do area definition using your structural connectivity contrast. And furthermore, why tractography is very powerful? It's also because you have several approaches to do invasive structural connectivity mapping by injecting different kind of radioactive compounds, for example, or do lesion studies, while actually tractography is the only, so far, in vivo tools that allows you to study these connections in vivo in a non-invasive way using just your MRI scanner. And what it comes down, what actually tractography is that it corresponds to the virtual dissection approach that has been used by anatomists to describe this white matter connectivity profile, but doing this, again, in an in vivo, non-invasive fashion using your diffusion MRI images. So that now you can segment white matter tracts using the diffusion MRI data that you've sampled during your experiment to perform what is known to be, again, the so-called in vivo virtual dissection. But of course, also tractography, like the diffusion tensor and like all the other models, is not perfect. So it's very nice because, like I just said, it's non-invasive. You can do it in vivo. You can map actually the whole brain, so you're not just constrained to a single postmortem slice or a single postmortem hemisphere and so on and so forth. But again, you can map the whole brain. You can address a series of questions like the ones that I presented to you at the beginning. But of course, it suffers from being low resolution, right? So we're bounded to the millimeter resolution that we acquire for, sitting behind the MRI scanner. It's indirect, once again, so always remember, it's water molecules here. It's not actually white matter axons that we're probing, that we get the signal from. It is error-prone. It is error-prone because of the presence of noise that we described before. And it's also very difficult, given all of these factors, to interpret it in a quantitative fashion. Right? I'm going to discuss about that a little bit later, but always remember that it's difficult to say area B is more strongly connected to area B rather than to area C, or compare across the different subjects. Now, how does tractography basically do? Like I hinted at before, using, for example, the simple DTI model is you're roughly connecting the dots. So you start from a seed region and you construct the path tangent to the principal diffusion direction. For the more mathematically inclined, this comes down to numerically solving this differential equation. So given certain starting conditions, certain starting position, such as the seed region that we defined there, we basically try to equate the derivative, the first derivative, so the tangent to the curve at a certain position with a principal eigenvector that we estimate out of a polynomial model, or in this case, out of a DTI model. And of course, the question becomes now, because this is what we do, these are all the algorithms that we do, that we program, that we set up while sitting behind our computers, the question becomes when to stop, right? So you initiate a streamline, but where should it track to, right? Should it go out of the brain? Should it transfer CSF regions, and so on and so forth? And a way to define, from an algorithmic perspective, a way to define stopping criteria can be imposing a certain curvature change threshold. So you don't want your streamline to suddenly bend at more than 90 degrees, for example. you can impose an anisotropy threshold. So using the combination with, for example, bowling stick and diffusion tensor model, you can say stop tracking when FA goes below 0.1, let's say, because low anisotropy means that it's probably an area of gray matter or even worse, CSF. Or you can impose some anatomical criteria, right? So let's say that you have defined a gray matter mask, and you basically just tell your algorithm stop tracking once you enter this mask, right? So only track when you're within white matter. And even if you do this very simple approach, you can get some very nice results. So once again, this is the Atlas example that I showed you at the very beginning. And using DTI, so-called deterministic tractography, so we haven't gone into the probabilistic part just of yet, but you can segment out the arcuate fasciculus, cingulate bundle, fornix, corticospinal tract, and so on and so forth, right? So even with this very simple tool, you can already do some pretty spectacular things. So just as a quick summary for this initial part, if you want to do DTI streamlined deterministic tractography, what you do is that you use the principal diffusion direction, so the main eigenvector out of your diffusion tensor estimate. You will propagate effectively the streamline until the criteria, the anatomical criteria, or the algorithmic criteria that you set up, and given these, basic, relatively simple approach, you can already reconstruct some major white matter fiber bundles. But let's now go back to this idea of uncertainty and reproducibility, right? So let's go back to the uncertainty cone that we had before, and let's say that I take one subject, and I put him or her in the scanner for 100 times, right? So I do 100 acquisition of exactly the same subject. How sure can I be, how certain can I be about my structural connectivity estimate? I can basically, given exactly the same seed point across all of these acquisitions of the same subject, I can launch my tractography algorithm, and I can derive such a map, such a reproducibility map, that basically tells me simply how many times have I gone through the same voxel, given all the acquisitions that I perform. And you see that if I just were to look about the nice 3D pictorial representation that I have here out of a single analysis of a single data set, I don't have a way to say which path is most likely than the other one, given that seed region. Well, actually, if I repeat the experiment hundreds of times, I see that I'm really sure that given the seed region, I will probably terminate somewhere here, but I'm very unlikely to project to the front or to the posterior part of the brain, right? So here we go back to this idea of uncertainty, and like in this case of reproducibility and producing a low and high reproducibility map. And how can we translate? Of course, we don't want to spend that much amount of money. We don't want to put the same subject in the scanner for hundreds of times. But how can we get similar path probability maps in this case? And basically one way to do this, and one way that we can do it using the bedpost-X, prop-X combination in FSL, is that, again, of course, we normally have only one data set from each and every scanner that we scanned. And what we can do is that we can use not a deterministic approach, like the one I presented when I was talking about the diffusion tensor, but we can use a probabilistic approach. So we recover the uncertainty in the fiber orientation using the framework that I described before, and I use this estimate of uncertainty to build the path probability map that I just introduced now. And what this basically means is I don't want to do just effectively a single streamlining, but if you remember, now in every voxel, I don't just have a single estimate of a principal diffusion direction, but I have a distribution of sticks. I have a distribution of orientations for all the fiber populations that I estimate. So now, given a starting point, I can start throwing thousands of streamlines, and each and every streamline will see a different estimate of a different orientation of that voxel, that in this voxel will be very constrained, but will explode in this voxel, for example. So I start throwing all the streamlines that I have, and this is roughly the result that I get. I don't have just one orientation, so a single streamline that will run upward, but I also have the fibers that will start fanning and reaching different areas of the cortex, thanks to the uncertainty estimate that I get out of bedpost 6. More precisely, well, in a cartoon example, how actually probabilistic cryptography works. This is a scenario, a brain scenario, that we can have out of a bedpost 6 analysis. So we have a series of voxels, a grid of 3x4 voxels, and now in each and every of these voxels, I have a distribution of sticks, distribution of anisotropic compartments, right? So how probabilistic cryptography works, given a question of is voxel B connected to voxel A, is that once again, it starts throwing thousands of streamlines, right? So we start from voxel A, we take one estimate of the principal diffusion direction, one stick out of the ensemble, out of the distribution of sticks that we have, and we start tracking, right? We reach the voxel boundary here, and we start seeing this voxel, right? We take one stick out of a distribution, and we keep tracking, right? Until we see another boundary, we see another voxel, and we do the same thing. We take one stick out of a distribution, and we keep tracking, right? So on and so forth, like this, for all of the boundaries. So this is our first streamline. We start again from voxel A, and we throw another one, but now at every step, every time that we encounter, every time that we enter a different voxel, we take another estimate, another stick estimate out of a distribution that we have, right? And if the first streamline didn't hit voxel B, the second one already does. But we actually want to do this in a more, well, we actually want to extract some quantitative connectivity information, so we do this again, hundreds and thousands of times, right? So that in the end, what we can get is we can compute the probability of A being connected to B as simply the ratio of the m streamlines that make it to B divided by the total number of streamlines that we initiated from A, right? So we don't have, like in the tensor deterministic case, a 0-1 information, connected versus non-connected, but we do have a weight, we do have a probabilistic likelihood of connection given the approach that I just described. Now let's see again, why is this uncertainty very important, and how can this uncertainty actually help us in modifying the connectivity weights? Let's now take the same grid, but imagine that between voxel A and voxel B, we see, well, let's say the ventricles, right? Where there's an explosion of uncertainty, water molecules are free to move in any possible direction. How does this affect our probabilistic result? What is going to happen is that, yes, maybe the first streamline will make it to B, but now given that we have a much higher uncertainty, a much wider distribution from which we can sample the orientations, this will tend to go all over the way, right? So if you think about before, now the connectivity between B and A is reduced just because you had this higher uncertainty area in between the two regions that you're interested in. So that's why the uncertainty estimate, that's how the uncertainty estimate can help you in determining the connectivity scores between the two voxels. And of course, this probabilistic approach can be expanded to the presence of multiple fibers in every voxel. And on the left-hand side is the case where you have, well, only one fiber population in every voxel. On the right-hand side, you have where you have up to 2 fiber populations in every voxel. And the only thing that you do in this case is that once you enter a new voxel, you don't sample just a fiber orientation from one population, but you sample out, well, 2 samples from the 2 distribution, and you select the one which is most collinear to the direction you entered in when you were coming from this voxel, and you just continue propagating the streamlines. Why is this useful? Why should we account actually for multiple fiber orientation in every voxel? Well, once again, because crossing occurs quite a lot at the resolution at which we sample our data. And let's take here an example in which you have fibers from the internal capsule projecting to the primary motor cortex, so the corticospinal tract fibers, and these are crossed at the centrum semivalley here by the superior longitudinal fasciculus in a 90-degree fashion. You see that for 9 subjects on the left-hand side, if you were not to account for the fiber crossings, you won't be able to reconstruct the lateral projections of the corticospinal tract. That you know that anatomically should be there, but you cannot see them if you have a crossing scenario and you don't account for it in your modeling. An even more severe case is fibers coming from the little geniculate nucleus and projecting to the primary auditory cortex, and which cross, again, let's say in a schematic 90-degree fashion with the optic radiation. In this case, if you're interested to virtually dissect the fibers reaching the primary auditory cortex, if you don't account for crossings in the same 9 subjects, basically you won't be able to see them, to extract them at all. So basically this is the way on how we can get our path probability maps. It tells us how reproducible, how sure we are about a structural connectivity between the seed region and the rest of the brain. They're often called in publication connection probability, connection strength, index, so on and so forth, but it doesn't tell you anything about the strength of the connectivity between 2 regions. It just tells you something about how reproducible your results in. So you should be very careful when comparing them in a population, in a subject population. And this is where the question comes in, right? But yes. 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 No, exactly. So this is the scenario that you're basically describing, right? So we're starting from here, we start propagating, and let's say we see this voxel, right? Yeah. So we do something like this. We take out, we have a distribution, we have a 2-fiber distribution. We take 1 stick from this distribution and 1 stick from the other distribution, right? So what you see is effectively this. And you propagate along the most collinear one, right? Because, again, it is true, maybe anatomically, these fibers can also take the 90-degree turn, but it is very unlikely, right? So what you tend to do is that you tend to follow the most collinear one, given a certain angular threshold. So to go back to the, well, one of the most interesting questions from a neuroanatomical point of view, what actually is, even from the anatomy point of view, what is a quantitative measure of connectivity? Is it the number of axons that connect 2 areas? Is it actually the relative proportion of axons that from the seed reach the target, so the probabilistic numbers that we get out of it? Or is it actually the integrity of this white matter connection? So degree of myelination along the path, conductivity, so on and so forth, you name it, packing density like here. The only thing that we have is actually the probability of a dominant pathway that we sample out of our diffusion field. It's the only information that we got. Yes, we get a probability, but it's not a given that will reflect any of the previously mentioned neuroanatomical measure of connectivity strength. What they actually depend on is that your probability, well, your estimated structural probability weights can depend on several factors that you're actually not interested in. Typically, the probabilities decay with the streamline length. So let's say that you're interested to track the fibers that run from the posterior to the anterior part of your brain. They need to travel quite a long distance. Given the noise in your measurement, they will go through areas which have different degrees of uncertainty, which can be high, low, and so on and so forth. So actually, you're going to get very low probability weights between the posterior and anterior part of your brain, but these just reflect the noise that you have in your data set. They don't reflect any neuroanatomical grounded concept of structural connectivity between the 2 areas. They can also reflect geometric complexity, right? Like in the example that I gave you before. We start seeding, we're very close to an area where uncertainty explodes, and just because of that, our probability weights will decay, will be lower once again. But it also depends on the resolution of the spatial grid, right? I said at the beginning that we always acquire, well, our data set at different millimeter resolutions, right? And given the sampling that you perform of your space, you're going to get different answers when it comes to probability weights. To give you, well, a more grounded way to see this dependence on the spatial resolution, try to imagine the probability maps that I saw before, so the volume, try to collapse that into an histogram, into the distribution of the probability weights. If you do that, if you just use a different histogram to represent exactly the same data, so you perform your streamlining at 2 mm resolution, but now you actually do the counting on a different grid. You resample your data set from, let's say, 2 mm isotropic to 200 millimeters cubes, right? And you once again count the number of streamlines that passes through, well, that nicer grid. And this is basically the only thing that, well, the main thing that track density imaging does. It regrids your original results. But even if you do this rather simple approach, it's going to act like a sort of super resolution algorithm. And now, given exactly the same structural connectivity mapping that you perform at the beginning, you start seeing the intersections, the crossing of the white matter fibers at a much higher resolution, with the corticospinal tract nicely crossing the callosal fibers, which are actually fanning to the contralateral hemisphere, right? So you can get these kind of results not by actually sampling 200 micron voxels, which not even the best scanner in the world can do at the moment, well, unless you're doing post-mortem rodent work, of course. But you can actually get that by using the structural connectivity information that tractography gives you. And just by simply collapsing these path probability maps to a one-dimensional histogram case, you basically observe where that results come from, right? So what we're doing here is giving the basically same histogram with many streamlines being sampled or few streamlines being sampled. We see that if we use a coarser grid, it becomes very difficult to distinguish the two different distributions of the histogram. Well, it actually becomes much more clear once we make the bins much smaller, which is exactly the same as regridding the original spatial grid that we have. But of course, you're also going to get, and this is the dependence of a structural connectivity weight on something that you're not interested in, the numbers, our probability weights will change depending on the grid size, on the binning size that we use. And another thing, of course, that is typically done when you do tractography studies is that you do add some prior knowledge before tracking. So this is typically translated in terms of different masks that you can use, waypoint exclusion and termination masks. And how basically this translates with how these are used into any experiment in which you're interested in extracting a certain white matter bundle. So that let's say that you're interested in extracting the corticospinal tract out of your patient or healthy population, right? You start seeding in the primary motor cortex. So place the seed in M1, specifically in the end area in this example. And if you were not to add any prior information, you see that, yes, the most likely path follows the corticospinal tract, but you also get some spurious fibers going through the corpus callosum and reaching the contralateral hemisphere, which you know shouldn't be there. So what you can do is that you can set an exclusion mask saying block all the fibers that cross the mid-sagittal plane, that go through the corpus callosum in this case. And this already gives you a much cleaner result. Another thing that you know from anatomy is that the corticospinal tract should go through a very narrow area, which is the so-known internal capsule. So you actually put a waypoint area, a waypoint region of interest, ROI, and you actually extract a much better picture, much better reliable picture of your corticospinal tract out of your single subject, like in this case. Another example, you're now interested in the corpus callosum, so the fibers that actually breach the contralateral hemisphere, but actually there you go. You get also this spurious connection along the corticospinal tract. And once again, what you can use here is the so-called waypoint mask. So you're actually telling the algorithm, only keep the streamlines. When you return the path probability maps, only retain the streamlines that go through the body of the corpus callosum, so through the green region, right? And there is the U-shaped corpus callosum. So, as a summary of this part, what probabilistic tractography needs is the uncertainty estimate that you get out of the Bayesian framework that we set up for bedpost sticks. What you effectively do, and this is why it can take a long time unless you have a GPU or graphic processing unit on your computer or server, is that you propagate thousands, hundreds of thousands of streamlines repetitively from a certain seed region, and what you get in the end is a connection probability between region A and region B. But once again, interpretation is tricky, right? This is a probability that you get out of your virtual streamlines, but should be handled with care and based on a certain hypothesis. So to conclude this talk, only 10 minutes later, briefly some basic tractography applications, right? So the the basic one being this idea of connectional contrast that you can get if you were to do a tractography reconstruction. So let's take a T1 weighted scan, a T1 weighted axial slice, like in this case from a subject. Beautiful contrast, very high resolution. But if you were to segment, if you were to extract the bilateral thalami, so the left and right thalamus, it becomes quite tricky, right? You have a very low signal to noise ratio, specifically in that area. What tractography is actually capable of giving you is this idea of connectional contrast. If you start seeding from the different voxels within the thalamus, you will see that depending on where you are, you will start projecting to different areas of the cortex, right? So if you start seeding from the ventrolateral nucleus of the thalamus, you will most likely reach the primary motor cortex, while if you start seeding from the mediodorsal nucleus of the thalamus, you are most likely going to reach the prefrontal cortex, right? Imagine that you apply these concepts throughout, the whole subcortical structure. You can get in vivo a map of the different nuclei of the thalamus, which are basically invisible when you perform a T1 weighted acquisition. So this is the idea, this is what we call the connectional contrast. And this approach has been used in a paper by Tim Behrens, where he basically used tractography to parcellate the thalamus in its different nuclei and validate that against well-known neuroanatomical knowledge. And of course, this has been taken and expanded to parcellate different areas, different cortical areas and different subcortical structures in other studies quite successfully, and while comparing to prior anatomical knowledge or between different species and try to look for homologous areas and regions. We can look, as I said before, and like we did in the baby connectome, you can look at structural brain development. So now you can combine the microstructure information that you get out of your diffusion-weighted data, so information about fractional isotropy, mean diffusivity, or more advanced model, the intraneurite water fraction, so which sort of measures what should be a proxy for axonal packing density, or the concept of fiber dispersion. And you can map these microstructural features to the different tracts that you're able to dissect in vivos from, in this case, the baby cohort, right? So you can compute an average within a certain mask, within a certain tract-specific mask, and now you can plot it on a temporal axis. So you have the different stages, different weeks of development, 38 weeks, 40 weeks, 44 weeks, which is the age at which the baby has been scanned. And if you were to put this tract-specific microstructural average and plot them against two microstructure informations, without any prior information about which tract category every single tract belongs to, so whether it's a projection tract, limbic tract, callosal tract, and so on and so forth, you see that in terms of development, they do form some nice clusters in terms of their microstructural features, pointing towards the fact that development happens at different time points. So different brain networks, different brain systems develop at different time points during early development, right? Being the main ones, of course, developing earlier, so motor, sensory networks developing at an earlier stage, and association areas being connected at a later stage of development, connected and myelinated at different stages of development. And what the arrow shows is the change, the rapid change in just a week time of these microstructural features in the baby cohort. So you see that you have quite massive and rapid change on a week-by-week basis. Another big question is, of course, okay, can we now trust these like beautiful, colorful results that we get out of tractography? The answer is always, of course, with care, given that our models are limited and tractography is limited per se. And we can imagine different scenarios in which our, well, diffusion direction estimate will fail. So let's say that, well, the most basic, the happy scenario in AVOX, in which we have a certain bundle of fibers running very nicely parallel and densely packed to each other, tensor and ball and stick model perform very well. But then you complicate the thing and you start having fibers fanning, and neither the tensor nor the principal diffusion direction that you get out of ball and stick will tell you anything. You get crossing, and the tensor doesn't tell you anything about it, but the ball and stick actually tells you that there are two fiber populations here. But if instead of crossing, you have two fibers, let's say, kissing, so still forming an X shape, but actually being completely independent between each other, even the ball and stick model will still give you the cross, but it won't tell you actually which path, which endpoint you should connect with each other. Or even fiber bending, it's going to be the same, because it will always see these two endpoints, right? So it will represent it as a cross rather than a sharp angle in that box, which will lead to some, of course, imprecision. So if we know that, if we now have a free region scenario and we know that this is actually the structural connectivity profile of them, what we're going to get with tractography via this voxel is that these regions now are not going to be connected, and we're going to have connection from this region to both of them, right? Because of the confounds that I just described. And near the cortex, these ambiguities or biases will actually explode, because then you have a very, well, narrow gyrus, which is going to sample in a matter of a couple of voxels, and you're unable to distinguish these sort of very sharp projections, right, that project to the so-called walls, rather than just to the top of the gyrus. And to try and circumvent this, we have developed, which is also in FSL, we have developed an asymmetric model of fiber orientation distribution, which is actually capable of distinguishing fanning from bending and also determine the so-called polarity of the fiber, right? So should it fan out or should it fan in? And if this is the symmetric answer that, well, any modern algorithm will give you, given these three different scenarios, this is what the asymmetric fiber orientation distributions will actually give you. So the cancellation of the spurious cross that we had there, it will retain the crossing in the case where it's actually justified, and it will give you the ice cream answer, which just basically represents the fiber fanning polarity, right? So fibers should fan along this orientation, while actually they should pack if you were to see it from the cortex itself. And we tested that on some simulations and also in vivo. And basically here is the different answer in 3 different ROIs on a myelin histological stains, so an actually post-mortem stain in which you can see where the accents go to, and those are the spurious or insufficient results that the symmetric analysis will give you, while if you use the asymmetric model, which is, again, just a simple modeling like we had the ball and stick before, you have the sharp bends here, but you also have the fiber fanning, correctly fanning there. So once again, different modeling approach, different answers, but they can help you when it comes to tracking results, when it comes to improving your tracking results. What you can do to validate your results is, of course, also to use multi-model approaches. So like in the Human Connectome project, you can use the functional data to interrogate structural functional relationship, because basically areas that are structurally connected to each other should communicate with each other. But actually what you get is that structural, because of a limitation of tractography and diffusion MRI analysis, you might get missing connection between two functionally connected areas. So if we look at this example at the bottom, we always do a seed approach, so seed connectivity approach at the bottom, using fMRI data, well, resting state fMRI data, task-based fMRI data, and diffusion tractography. And you see that seeding this from the same region will give you different connectivity profiles when it comes to the functional approaches and when it comes especially to comparing the structural results to the functional results. Well, actually, if you do invasive mapping of function and structure in, let's say, the macaque, you will get more coherent, well, as expected, results. And another thing, of course, from results that you can get out of tractography is the typical example of fiber crossing at the level of the cerebellum. So if you were to seed, if you're interested once again in the corticospinal tract, you know that fibers should decussate at the level of the bones. So seeding from one hemisphere should reach the contralateral cerebellar hemisphere. But actually, of course, because of the constraint that you impose with tractography, it will preferentially follow the most collinear path, ending in the ipsilateral cerebellar hemisphere, which is anatomically implausible. But even here, it's not that functional MRI can help you, because also functional MRI doesn't have a clue about laterality, right? So if it sees a correlated activation in both the hemispheres, it will give you that, right? So also fMRI is not capable of helping you in distinguishing this decussation behavior of white matter fibers. And that's all I had to say. Thanks very much for you to listening and to my collaborators. Cheers. Sure.
We were always talking about reducing this isotropic diffusion in white in gray matter. But in fact, the fibers are projecting into the gray matter.
Sure.
And they fund
Yeah.
different. So how can you
Yeah.
handle that?
So,
And
but
my second question is like, you have talked about the asymmetry approach.
Mhm.
What about the ball and rackets? Has this been the ball and rackets model?
Sure. So that is,
been implemented in SSL somehow, or it's just too
it's,
complex to?
it takes a very long time, unless you have because of the number of parameters that you need to estimate. You need, well, you definitely need a GPU to be able to estimate that, you know.
Is it available?
I'm not sure whether it's in the release. I should double check that, but I know that it should be there, or at least, well, we're planning to move like those kind of modeling to allow you to develop your own models in the new toolbox that we developed. That is called CUDIMod, and that is basically a microstructural modeling toolbox that allows you to come up with your model and then just compile it, just estimate it directly on the GPU in a very quick fashion. Because usually these approaches take a very long time, right? So if you come up with your own parametric way of analyzing diffusion MRI data, you just have to effectively write the equation, the model of your equation, and estimate the parameters out of that. So I need to double check about the ball and racket model, but this is the non-parametric approach of doing sort of what the ball and racket model does. So these go back to the spherical harmonics representation of a diffusion signal, and using basically the neighborhood information, we're capable of obtaining asymmetric fiber orientation functions. Right? This is how it roughly works. No, because again, this goes back to the idea of well, having an orthonormal basis defined on the sphere, right? So the spherical harmonics basis that we have. So it is a surface. It doesn't get you all the different parameters for the different fiber populations, but it kind of inherently does ARD, like in this example here. Yeah. So in gray matter, that's a good question. You would need, so there are more advanced models that are capable of analyzing data coming from gray matter. Just because in gray matter you have, like I said before, water more freely diffuses, but it's true, you do have a certain degree of anisotropy given by the fibers that enter the cortex. So yeah, you need more advanced modeling for that, but it's certainly possible. It's also a matter of resolution, right? So the human cortex ranges between what, 2 and 4 millimeter at max, yeah? So with current resolution, it's very tricky to get this nice insertion into the cortex. Yeah.
What about the probabilistic mass of derived from problem? So there is a way of threshold that can balance between two axon trajectories. it versus invalid or false positive results.
So you mean about, so not the BET-6, not the anisotropic volume fractions, but you can, let's say, threshold at 5%, but actually the path probability maps.
That the path probability.
So yeah, sure. You can also, so given that these are weighted representation of your paths, you can threshold them, and typical values range from 0.01 to, or, well, close to that, let's say, for a minimum. And that will already clean up your results quite a lot. But it's based on your pre-anatomical knowledge, basically, right? So it isn't a very much grounded. So the more grounded way is to apply approaches like using the different maps, the exclusion map, waypoint maps, and so on and so forth. And then, of course, visually checking the results to be able to remove false positive or false positive connection, right? But then it becomes a question, what is a false positive connection, right? Are you really sure that that weight will correspond to that? So,
I could imagine that it's easy to do on the cortical spinal tract,
Mhm.
but then to do, for example, on the
yeah, not even that,
should
probably,
be
yeah.
problematic.
Yeah, but that's why, but that's why you should go to the validation approaches, right?
Yes.
And try to, the golden idea would be, to define a threshold that works for all the connections. Yes.
The track density thing that you showed, the super cool, really involved, is that implemented in Amazon?
Yes, we do have that. Yeah.
And Matthew, I've never heard of it before, so that can be applied to sort of regular diffusion data, sort of 2 millimeter long filters?
Sure, absolutely. So I think, I'm not sure, but I think that was applied to 2 millimeter isotopic boxes. I mean, you can imagine, of course, that yes, if your base acquisition is amazing, like the HCP and like DHCP, this kind of data, you're going to get even better description than what you would get by regrading 2 millimeter data.
And can you combine that with the tractography probably?
Sure, so to get to track density images, you need to have run probabilistic
It's
tractography.
run off of,
Yeah, absolutely. Yeah, it's literally like a regrading of your path probability maps.
and then you can do metrics on.
But there are some people that do that. But, yeah. Yes. So you can use the waypoint masks, for example. Yeah, absolutely. But even if you do that, you're not effectively telling when you track, follow the path, which is now not the most collinear one, but it's actually the one that decussates, right? You're just saying retain those streamlines that reach that hemisphere, right? So you're removing the super strong connections, right, which get to the cerebral hemisphere that you're not interested in, but you just effectively boost the very low connections that you would otherwise get.
I'm sorry to interrupt.
No, I'm done.
We're gonna have 10 minutes of conflict.
Sure.
Eh? Cosa? Dove cazzo è il... Guarda che non c'è. Non c'era. Non riesco a portarla di qua. Ah, ok. Boh. È sotto. Yes.
Alright, so for those that didn't meet him already, here's Matteo Diano. Yes, basically if you do DIY, you're called Matteo, otherwise you cannot enter the field. He is coming from Turin, he's a postdoc working at the hospital
At the Molinette Hospital in Turin.
as a MRI technician and also postdoc at the University of Turin, and he's gonna talk about empirical validation of photography. So, Matteo, all yours. Thank you very much.
Thank you very much, Stefano. Thanks, Matteo, to gave a really nice talk before. And today I'm going to be the bad guy. I mean, because as a scientist, we need to be aware about limitation of these techniques that we use every day, and if it's possible to overcome them. The idea of this talk is to give you a brief overview of the limitation of stratigraphy specifically, and show you some methods that we can try to use it to find the right pathway in this jungle of streamlines. So, okay. So I'm going to talk about why we need to validate stratigraphy approach. I will show you, as I said, some methods to validate stratigraphy and fiber orientation estimation, such as software and hardware phantom, postmortem and biological samples, and challenges. With challenges, I mean the recent efforts that the scientific community made to test and validate stratigraphy and diffusion-weighted imaging. And of course, at the end, I will summarize the main findings that we learned from that. So we know that diffusion imaging is probably one of the, oh, this should be a video, but okay, perfect, it's not working. The diffusion imaging is probably the only method to study microstructure in the human white matter, and with that imaging techniques we can also calculate main trajectory and major axonal pathway. The first problem is it's for sure that we don't have any gold standard rules. Each group uses their configuration to perform stratigraphy, they calculate DVI indexes and so on. Differently, with the animals, we have some gold standards configuration, like approach. Like we can use neural tracer and see exactly the axonal pathway through the white matter. The invalidity of stratigraphy in humans came from different sources, such, for example, partial volume effect or crossing fiber issues. We also have to deal with other noise sources, such, for example, MRI artifacts and motion artifacts. And we have also to decide when we approach diffusion imaging, we have also to decide, for example, which is the best way to model fiber orientation. There are plenty of algorithms that we can use right now, and also as Matteo mentioned, we have a lot of criteria that we can use, especially in deterministic tractography, like, for example, define a certain amount of value of fractional anisotropy to stop the streamlines. So, why we need to validate? Well, it's science, of course. Scientists are continuous to modify, correct, and rebuild new theory that should be better explain the real biology, the real ground truth. I don't want to say anything bad on fMRI, for sure, but even this methodology that has been used for decades for study the human brain suffer from major controversies, such, for example, we still don't understand why it's necessary for our brain to increase the flow response after we deliver, for example, in the fMRI, we deliver a certain stimulus. One of the first methods that has been used to validate tractography and fiber orientation estimation is the software phantoms. Basically, the software phantom is a mathematical model that simulates diffusion signals with a well-known ground truth. With this simulation, we can test if the fiber's orientation algorithm is good to estimate the complex fiber geometry, and if tractography algorithm can track the right fiber bundles. However, there are some limitation on this approach, even if it's extremely flexible. Sometimes it's often to find some models that are basically constructed to show that a given algorithm is really good, and this software phantom also is so far away from the real biology of the brain. We don't know exactly how we cannot reproduce and mimic how a certain brain configuration can influence the diffusion weighting signal, for example. Another method that has been used in this field is the hardware or physical phantoms that provide basically a different balance between a ground truth control and the real signals. In fact, it's possible to control the factor that affect anisotropic water diffusion using, for example, different materials, and using also different fiber configuration. You can see region that we can use to estimate fiber orientation. However, we are still far away from real biology, and we don't know right now how to perfectly mimic axonal properties in this kind of phantom. To move close to the real biology of the brain, authors, scientists started to look at the postmortem tissues. It's not possible to control everything in this kind of sample, but this biological phantom provides physical properties that are close to the neural tissues. With this approach, it can be possible, for example, to scan the sample for a very long time, like days, weeks, months, without making anything bad to the sample. And also the other advantage is that we don't have any motion artifacts and other artifacts related to the MRI acquisition. Another important advantage that we can use, we can obtain histological information from the tissues. And so we can compare this information with our tractography. Here I want to show you a classical example of post-mortem dissection. In this case, the goal was to identify a real tract in the post-mortem brain, the human brain, and compare it with the results of the diffusion weighted imaging on the healthy subject. So this procedure involves a series of steps in which the brain needs to be fixated, then cleaned from non-brain tissues, some like arachnoid membrane and vessels. Then the refrigeration step, it's really important because allow to better identify axonal pathway causing axon to swell, and help also to remove gray matter cortex. Then, after we've done these steps, we can start to dissect the brain and identify major tracts. And use these tools, we can extract from the brain the tracts. Like here, we can compare this tract with the tractography results and see how they different. We can also compute and calculate false positive and overlap ratio and other many indexes that tell us how confident was our algorithms respect to the real biology. Another example of post-mortem the biological phantom is from Catani's group, that they studied geometry accuracy of DTI tractography and DTI indexes in ex vivo human cerebellum with a super resolution of 100 micrometers. With this sufficient resolution and signal, it's possible to say that, and it's possible to see that DVI signals, like here, okay, thanks. DVI signals and DVI indexes, sorry, can differentiate from the gray matter, the third layer of the gray matter, and the first one, and the white matter. And also tractography can reveal some precise pathway related to granular cell and T junction in the cerebellum. While this technique is promising, we have to consider some limitation. For example, fixating the brain modify water diffusion, which inevitable change some biological properties of the tissues. The T2 relaxation is shorter, and we need custom sequences and coils to able to achieve some signal. Also, the tissue preparation require an incredible manual skill, because there is a high risk to modify this inner geometry. For example, by squeezing the brain or just moving the brain to one place to the other. The time needed for scanning is incredibly long, and I'm sure that your colleagues will sure complain about it, because you will occupy the scan for days and weeks. and the operator has to have a precise knowledge of the neuroanatomy, and this procedure is still subjective on human error during the dissection procedure. So, due to the relevance of fiber tractography to investigate human function, one way for sure is to validate, one alternative way to validate tractography is to ask the scientific community to participate at a public organized challenge. In this way, for example, an algorithm or solution may be developed to address a specific challenge or specific issue in this field. Now, in this section, I'm going to show you the major competition in this field and their goals. I'm not going to show you final results of this competition because I don't have time to explain in details each competition and their results. And also, it's your duty as a scientist to find optimal way to address your research question. So the first one, FiberCop, was the first community effort to try and get some quantitative evaluation of tractography algorithms on a common dataset, on a physical phantom. This challenge was to find 16 existing connections on this phantom, and using a predefined ROI, a voxels ROI. So you can see here the ground truth is well defined with some stemming fibers, kissing fibers, configuration, crossing, and curvature, and so on. So the participant has been, they deliver this phantom to the participant and ask them to calculate and use their algorithm to perform tractography. In this example, you can see here, like, how can I, no? You can see here, I don't know if you can see, but there are the 16 voxels, ROI voxels. Below, it's the ground truth that we expected to find, basically. They expected to find the fiber. And here, you can see some results. For example, in the upper part, on the left, in this position, you can see that all the algorithms track the right fiber bundles. However, one was incorrect. There are some limitations in this challenge that we need to take care. First, this challenge was limited to deterministic tractography, and also, as I mentioned, these physical phantoms differ from living tissues, and diffusion here occurred only in the extracellular compartment. One really nice aspect of this competition was that the researcher didn't know the real fiber geometry of these phantoms, so they basically tracked streamlines and hope that was in the right position. Another interesting challenge was the DTI challenge. That objective was to reconstruct the best corticospinal tract as judged by a panel of experts. The corticospinal tract was chosen because it's one of the well-known tract in human that has its anatomical origin and termination. Interestingly, the data, these are real data. The data also came from patients with glioma that cause near the corticospinal tract that cause partial volume effect and distortion and volume distortion in one of the cortical spinal tract. So the judge can also distinguish and see by compare the healthy corticospinal tract with the not healthy corticospinal tract. They compare and validate tractography. So the judges have to decide about accuracy of the submission and also about the speed and reliability of the process. They basically ask the participant to pre-process and estimate tractography in front of them at the conference. I don't remember which one, maybe Mikai or don't remember. Another real interesting challenge was the tractography challenge. The goal was to provide the best possible reconstruction or set of fiber pathways in a realistic simulated replication of the whole human brain diffusion that are with properties that are typically of a clinical acquisition. So this was achieved by manually estimating and segmenting 25 fiber bundles in a healthy subject. They use one subject from Human Connectome project. Then this estimation was used to create a ground truth background for creating a synthetic fiber bundles. You can see here all the steps that they have done. So segment a certain fiber bundles, then use it as a ground truth for creating a synthetic bundle model, and then combine these 25 tract to create the wall diffusion brain. And they ask for sure to the participant to estimate these 25 fiber bundles. The results are quite impressive. I just show you this slide that it's that show only a few results of the huge research. So basically you can see they evaluate valid connection versus invalid connection, and also some measure from volume-based of bundle overlap and bundle overreach. Here, this percentage indicates the overlay ratio, and this one the overreach ratio. You can see, for example, on the corticospinal tract that DTI-based deterministic tractography covered overlay 20% of the corticospinal tract, but the overreach was the 3%. If you move to a probabilistic approach based on the RD acquisition, you can see that overlay is increased, while also the overreach. So overreach means that the fiber bundles that are outside the ground truth bundles. Another challenge was the RD reconstruction challenge. This challenge focused on validating the local fiber orientation distribution, finding which algorithm was the best one to local estimate single and fiber and crossing configuration. The results varies from the algorithm that they use to calculate this fiber orientation, that range from the standard DTI. You can see here the ground truth of the fiber in one box. So, and here you can see the fiber estimation model from DTI or Q-ball imaging, constraint spherical deconvolution, and so on. So this challenge was just to try to find the best, the optimal algorithm to reconstruct the fiber orientation. Another challenge was the stratigraphy reproducibility challenge with empirical data. The goal was of this challenge was to assess the reproducibility of emerging pipelines that has been used in the clinical practice. So they asked the participant to track 10 white matter bundles on a single subject data that came from 2 different scanners. And in each scanner, they perform 5 runs of diffusion-weighted imaging. Each tracks here was evaluated using a dice coefficient to look the coherence of tracks within session, across session, and across scanner. The last but not least was the really recent the 3D validation of stratigraphy with experimental MRI. This challenge was based on 3 different validation strategies. One using a physical phantom with 16 fiber bundles, an high resolution ex vivo macaque dataset with an atlas of known connection, and also an ex vivo squirrel monkeys with the histological tracer injection. The challenge was to estimate the ground truth bundles and connection in all database. Here is just an example of one results with different submission. You can see here it's quite different from that one, and so on. They evaluate pipeline on to process diffusion weighted imaging, algorithms, and fiber orientation. So what we learned from this challenge was that this is a really good news, that diffusion stratigraphy is able to reconstruct valid fiber bundles, and these connections are typically very close to spatially to the ground truth. However, there are some limitations that we need to take in account. For example, when our algorithm finds crossing fiber region, that sometimes there are some incorrect streamlines that we can find and track incorrect streamlines. We unfortunately have a low overall bundle coverage and low % of valid connection. Another limitation is that use stratigraphy in neurosurgical decision is very challenging because we have a large variabilities across among algorithms, and the present we have a huge presence of false negative pathways. Another good news that we are really good to estimate local orientation. So our algorithms right now are able to detect different fiber configuration, and the stratigraphy is reproducible. Sorry, but algorithms can give you a very different results. Thank you. I don't know how to. Wait a sec. Sorry, just need to.
Try plugging.
Yeah, I don't know why it's so fucking small over there. Look.
Oh, we don't have a... Oops. No, it was me. Vicente, ¿puedes venir? ¿No tiene conexión a internet? Para
Just one thing, if you have downloaded the presentation in PowerPoint, please delete it. I will download a PDF, okay? The one you see.
Dime. Dale ahí. Eso es.
Okay.
Y cuando salga lo del ring, le das a un botón que pone hacer.
¿No hay acceso al repositorio aquí?
¿Eh?
¿No hay acceso al repositorio directamente aquí?
No, tienes que meterte en... Pero no, yo no lo tengo en el repositorio, lo tienes tú. La tuya, la pasaste, pero la presentation.
Sí. Bueno, te lo he pasado hace 3 o 4 horas cuando te lo dije.
¿Qué?
Te lo he pasado hace 3 o 4 horas cuando te lo dije.
No sé si la tengo.
No,
Si no, bájatela tú.
pero es que no sale nada.
Tiene que haber un...
Que no sale lo de la conexión.
Ay,
¿Dónde se pone esto?
un segundo. Eso de ahí. No, pero ya, creo que ya tienes internet, ¿no? Si tienes internet. Deberías poder... Pues,
Con el
no.
Fimbra.
You have it connected to the BCBL network or eDROM, do so also. Because we are too many people right now.
Internet open.
A ver, joder. Que no le carga el internet. internet doesn't work and I don't know why. I'm gonna call Duguti,
Which internet?
the one from the BrainHack network, but the thing is that he needs that one.
Let's go for it.
Don't worry. Yeah. So are you planning to go somewhere? Okay. Sorry guys.
No va, ¿no? Guti, se me ha desconectado el BrainHack 2019 del ordenador principal y no va el internet, o sea, no le deja loguear. ¿Sabes? O sea, yo me conecto desde el ordenador que me dejaste al BrainHack 2019 y cuando va a intentar loguear no carga la página web. Sé que hay un problema. El ordenador o bueno, puedo intentarlo. He reiniciado la conexión. Vale, reinicia el ordenador. Anda.
Ok.
Vale, pues vamos a probar a ver y si no... Vale. Bueno, estas cosas surgen cuando menos se lo espera.
Si no pongo mi ordenador, ¿no?
Sí, también. Total, ahora no tenemos el streaming de la pantalla, así que podemos hacerlo desde el tuyo. ¿Tienes instalada Virtual Machine?
Bueno, no, pero no la necesito realmente. Lo que pasa es que va a ser un coñazo para ponerlo.
Si quieres, haz la presentación con tu ordenador mientras tanto.
Espérate, si va, lo hacemos aquí. Si no,
Vale.
cojo mi ordenador directamente y lo hago todo ahí, que va a ser mejor para el trap y para todo.
Total, si es que... Venga. A ver. Wifi. Joder, cállate, coño.
Que vaya mierda de ordenador andado.
El que había. Pero sí, continúa, a ver. Esta es la primera... Mira, vale, ya está. A tomar por culo, ya lo tienes.
A ver. CDL.
Ok.
¿Cómo se pone la arroba aquí? La arroba.
Arroba, tío, shift arroba. Shift arroba. No hace falta que... Con el username basta, tío. No hace falta que pongas el arroba. Tira, tú puedes dar cuenta que... ¿Nunca lo has visto así? Pues...
Ok.
Vale, ¿puedes mandarme el correo ese directo a mí?
Te lo he mandado a ti ya.
Sí, pues no sé si lo tengo. No lo tengo. O sea, ¿me la acabas de mandar ahora? ¿Seguro?
¿Eh?
¿Me la acabas de mandar
Te lo he
ahora?
mandado hace un rato. No, ¿por qué no se ve hoy?
Porque... Espera. Ponle...
So I'm Carlos. I work here in the BCBL. First, thanks both Mateos for the nice talks. It was very clear, very nice. My humble contribution will be about dissecting in vivo white matter tracks based on deterministic tractography. I will be using a region of interest approach, a manual region of interest approach. That is supposed to be better for the pathological brain because it accounts better for inter-individual comparisons. And well, basically, it's more time-consuming. That's the bad point, and you need high a priori anatomical knowledge to perform it. So my goal was to provide a very, very, very basic pipeline to start playing with tractography. You can try at home. So from the raw data, you can transfer your DICOM files to Nifty. And if you use MRI Crow of MRI Convert, you will get the B-ball and B-vector text files that contains basically the gradient directions and the B values that are the weighting, the diffusion weightings. And you can use Explore DTI, that is open source, to perform a basic preprocessing. You can correct for subject motion distortion and for geometrical distortion. And you can convert it in a math file that is compatible with Star Trek, that is a software developed by Flavio Del Agua that has a series of deterministic algorithms based on spherical deconvolution that derives in a HMOA index that is specially indicated for resolving crossing fibers, as Matteo was explaining before. So basically, using this software, you can fine-tune the algorithm with parameters. You can play a bit with the length, with the threshold, and all of that. And then you get a tractography file that is compatible with TrackBiz. You also will get the CS, the convergent speed maps, the mean diffusivity, and the fractional isotropy maps that are indexes that Matteo explained before. So let's try to open TrackBiz in the virtual machine. I hope it worked well. Okay. Make sure you have this option tick. Otherwise you won't be able to run TrackBiz. No, solo estaba abierto. Entonces ahora debería ir, ¿no? ¿Hay eco?
Sí, sí, estás en la red de BrainHack.
Okay. Sigue sin ir.
¿Estás en la red de BrainHack?
Sí, se supone que sí. Sorry guys for the technical problems.
¿Puedes seguir sin nada esto?
Sí. So this is a software that is really easy to use. It's called TrackBeast, in which basically you have 3 panels. One visualizer render that is the one in which you are seeing a sample of the tractography. As I said, this is a deterministic tractography, so it's let's say a final estimation of the fiber direction based on a spherical deconvolution. So you will see a sample just to save computational resources that is thresholded. And the first thing you can do here is delete it, because if not, it's going to be slow. And then you can load, click to this, you can load a map, a scalar map that you choose. In this case, a CSHMOA map that indicates the decay, the speed of the decay of the fitting error between the fiber model estimation and the diffusion tensor within each voxel. So you, in the bottom part, you have the images in which you are going to work. And basically it works like manually drawing region of interest. So the first thing you can do in this program is just making a sphere. And you can move it for each axis and just explore what happened when you put the sphere there in the render panel. So in this case, for instance, you have the sphere in the pons, so you can see the corona radiata. And for instance, you put it here. Do you know what track is it? The Singulum bundle. So you can play a bit just with the ball to see what happened. Then this work with ROIs that work like logical operators. So you basically tell the program, please give me a track in this tractography that passed through here or through here. So you can provide with as many ROIs as you want. And you can also create a not ROI, so it is like a constraint. So you can say the program, please tell me give me a track that passed through here and through here, but not through here. So, for instance, a way to do this, it will be like drawing this small ROI on the bottom of the corpus callosum, and tell the program, give me everything that passed through here. And you will see something like that. You know what track this is? Sorry? Yeah. You got the fornice part of other tracks. So what you can do is creating a not ROI. For instance, if you don't want the fibers that go to the bottom of the brain, and tell the program, please remove everything that passed through here, and you will get a cleaner, let's say, fornix. Yeah. So with this, you can go to the statistics slash, and then you have a histogram basically in which you can select the scalar, so the index that is based on the map you have chosen. And you can, for instance, see for the mean HMOA, that is the index of diffusivity I've chosen. And then you can export it in a TXT file for doing your statistics. Also, you can create nice renders to create images. You can do it by, for instance, render it like a tube, giving it different colors, giving it, for instance, a scalar, in which you can represent the index with a color code. And yeah, just that. I've uploaded in the material MNI normalized template that you can use. It's so fast to do it. This is the one I wanted to use, but the virtual machine is not working. So you can try first to do that there. It's going to be easy because it's so smooth and so clear. Then you have a real example of a patient in the materials. You can see a real example of a patient in the materials that have a meningioma. And I encourage you to try to dissect the superior longitudinal fascicle with this method. You will see a surprise. So you will see basically that the meningioma is pushing the truss that you are trying to dissect. And yeah, just that. Sorry, we could not do it with the virtual machine. So to use this approach, you need a prior anatomical knowledge. So you can also use a series of atlases that are available online. One that is very common is the one of Catani and Thibault. And James will be talking about that later. And also in the materials, you can find supplementary materials of a paper by Michel Thibault, in which is very nicely explained how can you do it and what kind of ROIs you can draw to find the major wet matter tracks. So thank you.
sake of talking about white matter, I don't know, a year or two ago, and Stefano pulled me into BrainHack. So I feel very shy to talk about anything with people like the gurus, Mateos here. But anyway, so if you're like me, I take things very literally. So when people say there's a map of white matter, I think, oh, it's an actual map, like a road map. But what it seems to me is our maps are still not so great. So this is a very ancient Greek map, which basically said that the world is the Mediterranean, and that was it, right, a couple thousand years ago. And sometimes when I read papers on the hippocampus, I think it's a bit like this. People just say, oh, the hippocampus and then the rest of the brain. Like, oh, okay. Just to give you, this is just for fun. This is an ancient Korean map from the 1400s. This is basically China. This is something vaguely like India, and that's Africa with a giant lake in the middle of it. This is a map from the 1500s. It's pretty good, actually, in some ways. Australia, you see, is completely missing. Antarctica is a little bit larger than it should be, maybe. And this kind of stuff is pretty distorted compared to what it looks like today. And this is a little bit better in the 1700s. Antarctica is completely missing, and Australia is only partly there. And I just did this for fun, just because it seems to me that when you compare it to modern stuff, like this is NASA has a satellite out there which takes pictures of the Earth all day, every day now. It's pretty accurate from a mapping point of view. And this is if you play around with Google Earth. That's our building right here. And you can go out, you know, there's the world, which you all know very well. And you come back around and you can kind of zoom back in. So our idea of what maps means in normal English now is very advanced, right? You pull out Google Maps, you can pretty much find yourself anywhere in the world. But if you say, where are you in the brain with your white matter atlases, I found it very frustrating. So then I started looking for different ones. We look at so what I'm going to do just now, this is all very brief and kind of superficial in a way, but it's just to give you an idea of, and if anybody knows of better atlases, better maps of white matter in the brain, please tell me. There's two built into FSL. There's Katani's and Thibaut de Chotin's Nat Brain Lab Atlas. Michel has made a new one, which is it's very interesting, it's a bit different. Tracula, of course, has its kind of built-in frame of reference. And then I came across something from Chicago, which I found very interesting. So the Maury's work, and I mean, I feel funny talking about people like this, because these are like the gods in heaven to me. You know, these are it's like Matteo. It's like, oh, these are the guys who really know about white matter. I only know a little bit. And so this map is a few years old. And you see, though, that it's got it doesn't have all this here. There's two different ones. One is the one with the 20 main tracks, which is similar to what's in Tracula. The Labels Atlas has 48 shorter tracks. There's 2005, so it's a little over 10 years old, almost 15 years old now. And then what I did is for each of these, what I did is I took, using FSL primarily, the MNI template space. I ran fast, which is the segmentation on it, right? So you just get just the white matter, more or less. And then I want to see, all right, if you take all of the tracks in each of these atlases, so I'm not going to talk about any specific track, I just say, give me all the tracks, how much of the white matter in the brain are we actually mapping? Okay, and so in each one, I didn't do anything to do with the actual tracks. So there's the white matter, roughly speaking, colored. Something that I just want to point out is if you see here, down at the base of the forebrain, you can see, now this is where the pointer would actually, if you could show me how to use this, Stefano, that would be helpful. I don't know how this thing works. But basically you can see that parts of the forebrain white matter are not actually in the segmentation. And if you look over at the fornix, you'll see the same thing. So you just need to be careful, even with what's considered, I gather, the best white matter segmentation algorithm in the business. It still misses a bit on the edges some places. So it depends what you're mapping. All right, so now if we put this back, this is the the 18 major tracks, just running through the brain there, and you can see wherever it's blue is where the atlas doesn't cover the white matter. Okay, and trust me, I've used this a lot, this atlas. So it's very widely known about. And then if you switch over, of course, there's 3 different threshold levels in Maury's 20 things, right? There's the 0, sort of 75% and 50% overlap, but it gets quite small with the lower thresholds. And then if you look at the labels map, you'll see that the labels map actually is only covering the sort of central portion of the brain. Right? So even though it looks, 48 compared to 20, an idiot like me thinks, oh, that's great, there must be more of the brain. Not really the case. And this is just a 3D using MRI, micro GL, just showing you. So the 3 different threshold levels in the Maury Atlas of the 18 tracks. The gray is actually the bigger version, and then the red is the smaller version, and the yellow is even smaller still. And this is the labels. Now this is the green is showing what does the labels atlas cover relative to the 0 threshold of the tracks atlas, right? So just to give you an idea. And for me anyway, this kind of globalish sort of overview has helped quite a lot, because then it made me understand, be really careful when you do this stuff, because if you're going to use the atlas as your guide, you're looking at a small portion. This is exactly the same atlas that Matteo is now talking about. Is very famous. Some people say this is why Cortex has such a high impact factor, because of this one paper that's been cited a zillion times. And this, I think, Matteo will correct me if I'm wrong, but this was quite a breakthrough, this paper, in terms of giving some sort of standardization to white matter track location. And that's only, it's 2019 now, it's 2008, it's basically like 10 years ago. So in terms of where the field is at, it's all quite recent to start to get even this level of information. So you can download the digitized version of this atlas now, which didn't exist when the Cortex paper came out. If you go to Professor Gattani's lab, the one that he and Michel created, there's a close-up, and if you look at the paper and you look at which are the groups here, basically it's very, very similar, except now they've segmented some subsections of some of the tracks. And doing the same trick here, this one I'll just let run, but you can see a lot of the white matter is not actually covered by the atlas. So again, worth keeping in mind when you're thinking about, okay, I can use the Gattani atlas that's going to cover the brain. Well, it covers a lot of the brain, but it leaves out some significant portions. This is just another version of it to see it in 3D. It's a little bit not so useful maybe, but nonetheless, where it's gray, it means that the atlas isn't covering what's on that thing. All right, now here's Michel Thibault de Chotin's lab page, and he again very nicely has created a software package you can download for free, and within it is the see it's beautiful. It's like an Apple version, Linux version. This is the recent paper where they published this thing called the BCB toolkit. Here we go. Not BCBL, but BCB toolkit. And within it is contained his version of the atlas. And you'll see it's a bit different because it covers, it leaves out the cerebellum completely, but it's much more complete in one way, but at the same time it's problematic because it covers the gray matter in the ventricles. So you can see where the gray matter outline is here. And then if you zoom in on the ventricle over here, you will see that the atlas is actually covering up the ventricle. So if you're going to use this atlas, even to the individual tracks, you have to mask out the gray matter in the ventricles quite carefully. And some of the individual tracks, like the anterior commissure, for instance, in the original one and this one are a bit different from each other. And it's not so clear to me, and the fornix as well, it's not so clear to me what the explanation is for why you have such a different shape of the track. It's not that the shape is like bigger or longer or something like that. Here is Tracula, which is extremely well known in the FSL universe. Tracula is very cool in the sense that you get to use it with your free surfer segmentation and parcellation and everything. But it's a funny animal because it's basically built off of FSL. It runs FSL, and it kind of runs it in a preset way. So it's a bit tricky to hack it and play with it because sometimes it crashes. You kind of have to use it the way Anastasia has set it up. But here is just this is a different kind of map, but here's an FA map created using Dracula's preprocessing. And then here's a combination showing the parts of the map that the tractography covers. And you see, again, it's leaving out quite a lot. And no offense to Anastasia, it's beautiful what they built, but they're calling it global tractography, but that's, in my view, not exactly. You've left out a lot of the brain. And similarly with the 18 major tracks, or 20, of Maury's thing, you're leaving out a lot of tracks that are in the brain that are really important. Tracks that in the neurology literature, if you cut some of those tracks which are not in your atlases, you can't perform certain basic cognitive functions. So the last one, that's why I said this is going to be a fairly quick talk because it's the end of the day too. I was just hunting around because I was actually looking for atlas versions of certain tracks and finding them quite difficult to find. And in particular, I was looking for the fornix at one point. And I found a reference in some paper to these guys at the Illinois Institute of Technology in Chicago. And here's their sort of main paper. This is the fellow here, Athanakis, another Greek guy, who's sort of in charge of the whole thing. And you can also download this one. Now, their major bundle one looks similar to like Maury's 18 tracks, major tracks, or a little bit like the Tracula one. You can move it along. You don't really need to take so long. However, if you go to the complete one, and I actually wondered whether maybe the Oxford, your universe, you should start to negotiate to add this, because look at the coverage compared to the other ones. It's still missing, but you know, these are average spaces and so on. But it's a much more thorough coverage of the white matter than the other atlases that I've found so far. And like I say, if other people have better atlases, please tell me. And for someone who's as naive as I am coming into this, wanting to understand, I mean, I'm sure most of you guys, if you've done any work in the universe of tractography, you know, the number of papers that show you different map of the uncinate fasciculus, for instance. You know, you get another paper comes out and says, well, actually, no, we found that the uncinate also goes into this part of the prefrontal cortex. We found this part goes into the basolateral forebrain. Well, it reaches a little bit differently into the temporal lobe than the previous papers have shown. So there's so much uncertainty. And when I think about the rest of the body, you know, we don't have a lot of uncertainty where your heart or your lungs are. Everybody's pretty common. We're sort of pretty certain where they are. But in terms of where the tracks are in the brain, even though people say, well, we know now where the major tracks are, if you read all the literature, you find again and again and again, well, no, the cingulin bundle ends in the forebrain in this part, or, you know, it's very frustrating to me. And so at least if we could get a complete consensus atlas of the white matter, I think that would be very helpful to the field going forward. Anyway, so that's basically it. So what we want to get to is more like, that's from Google today, or 2 days ago, classic National Geographic map of the world. And that's it. Thanks.